because then it gets abstract and very hard to follow. We are lucky that a lot of people in this room have been part of the SWUS project, including a part of the TI team and Gabe Toro from the PPRP. But for the rest of the PPRP, this is mostly new. And for other people in the assistance as well, this is new. And we need to make sure everybody's on board with this and it's understood and that we can move forward. So we'll start with Norm, and you will see we left a lot of time for discussion to really make sure that we go through Nico's talks today. So Norm, I'll start your slides since I'm here. Oh, they don't want the slides. Yes, okay. What's this? Oh, Norm didn't prepare his slides? I don't know why. Let me try again. Yes, I can see that. You're smiling. There you go.
Good morning. I think many of you were here. We talked about this for SWUS in March and spent probably a whole morning on the topic. What I'm trying to do to start off is to show you that this is actually really straightforward and is the natural evolution of what we've been doing over the last 20 years, almost returning to where we started this process, okay? So it's going to be simple. That's my goal to talk to you about it. So when we talk about epistemic uncertainty, when we were dealing with this in the 90s and in the first applications of SHAC, we were thinking of, we have not an allegory, but an epistemic distribution, and we're discretizing that, right? So just think of a simple distribution here. I'm going to discretize it. We typically downsample tremendously to 3 points in our distribution, shown here on the red, that will recover the mean and the variance of the distribution. So we'll generally be putting the mean and then the 5 and the 95% numbers. And so often we would be asked for, what are your 5, 50th, and 95th fractal estimates on the uncertainty? But the concept was we were discretizing a continuous distribution and trying to get weights that represented probabilities. Okay, that's what was built into the model. So I'll talk about projects that I know something about. There's probably other ones, but level 3 and level 4 ground motion studies, starting with the TIP project, which was from Livermore in the mid-90s, Yucca Mtn, the EPRI 2004 ground motion model, PEGASOS, BCHYDRO, SWUS. I didn't put Hanford in there. They're doing this as well. I'll talk about it at the very end because I don't know all the details. I should not have said Hanford. I think that's what did it. So other people here know about Hanford and can add to the discussion if that comes up. So we'll start with TIP. So this was a trial implementation of the SHAC process, of the SHAC level 4, and the idea was very much of expert elicitation. You go to some expert in ground motion who just knows the answer, right? They can divine it, and you say, what's the median spectral acceleration for 5 hertz from a 1906 earthquake at 20 kilometers away from a rock site? And you say, they give you a scalar answer, okay, for that particular magnitude, distance, and frequency. They'll say his best estimate is 0.2 G, okay, and then you ask them, give me the 50th, and 95th uncertainty values for that, okay? And so then they'll give you the range, maybe between 0.05 G and half a G, centered at 0.2 G, something like that. The concept then is, this is a full distribution. We really have mutually exclusive, collectively exhaustive distribution that we're simply downsizing to 3 to make our life simple, right? But that's our numerical estimate of the entire distribution. So we would get 3 points like this on a continuous distribution. We draw their, they come up with things and say, this is what you're implying, is this right, and so forth. But the idea was really this concept of expert elicitation that came from other fields at the time where the experts just knew, and if you could probe their brain and get in there, you could pull out the right answer, right? This was how could you ask questions and get the right answer out. We tried something like that on Yucca Mountain, okay? Many of you were involved with this. We ran into some problems, but the same idea. We get the experts to consider many discrete magnitude and distance cases. We had a bunch of them, and then we wanted them to look at the cases individually and apply their judgments to those cases so that we got what is the right distribution that's coming out of the whole thing, okay? Showing that, again, the epistemic distribution is appropriate. How do they know it's appropriate? They're experts, right? They are qualified to do that. So we'd ask the same type of a question, what's the specific ground motion? And we did about 60 magnitude and distance pairs and 9 frequencies. And we did horizontal and vertical. So the answer for each was a scalar number. Here's the value. And instead of asking for the 5th, 50th, and 95th fractiles, we were going to be more clever and say, give us the whole distribution. So we asked for the mu median. Then we had a sigma mu plus and a sigma mu minus because the distribution was allowed to be asymmetric. Again, we have a complete distribution, okay, so that if you downsample that, you'd be back to mutually exclusive, collectively exhaustive description of the answer. So everything was there. Okay, this didn't work quite so well, all right? Any ideas why? Do you think you know? Okay, so this is the kind of thing that came out of this. This is our sigma mu's. In this case, they were the same values were there, but at this distance, it was more uncertain at short distances, more uncertain at long distances. In those days, this was sort of the center of the data, around 30 kilometers, so that was our best estimate, and there's a range of values here, okay? Difficulties. We are asking them to do way too many things. You can't ask someone to give you 540 cases, horizontal and vertical, over 1,000 cases, and pay attention to each one and divine the answer, right? So what did they do? They all used some algorithm to get to those things. They all ended up putting weights on alternative models and just said, whatever comes out, use it. Okay, so the algorithms were based on relative merit weights of the problem. Okay, so it's back to not fundamentally probabilities, but this model has more advantages or strengths than this other model. I'll give it twice the weight. Okay, we included numerical simulations. We included finite fault simulations, point source simulations. We had GMPEs. And the answers were intended to be a description of the statistical distribution, but really we had shifted from this concept of let me describe the whole thing to relative of probabilities to relative merits of alternative models. And so we lost that whole problem or that whole concept that we were trying to get at. So we are no longer, and we also had results independent, so there was no really correlation between the cases that were done. All of them also used symmetric distributions. We gave them the option to do it asymmetric. The problem was the workload was too much. Okay, so that really didn't work so well. In EPRI 2004 was a SHAC level 3. The concept evolved a little bit here. So instead of, it had 2 parts. There were model clusters based on approaches to modeling like single corner stochastic model, double corner stochastic model, hybrid empirical, and finite fault. I think Bob's telling me that's right. Okay, so you had clusters, and then within each cluster there was actually the statistical uncertainty was addressed within each cluster. So then the questions are, what are the weights for the cluster, and what are the weights for the GMPEs within a cluster when you make a suite of them? So it's a vector now as your answer. It's not a single scalar, but you're trying to make the GMP answer a whole lot of problems. Okay. For the weights for the clusters, we're back to merits of approaches. Okay. finite fault simulation should be, given higher weight? Does it have better seismological basis to it? Does it have more data to it, and so forth, and those things? They weren't really the probabilities that those models were right. They're back to merits on those. Within the cluster, it was back to a representative set of GMPEs is generated, and weights that are now really discretizing a continuous distribution. Okay, what is the suite of models? Somewhat like what we showed yesterday, when you just take a covariance of the parameter space or coefficient space, and you generate sets of models that can go in there. So the clusters then are evaluated for merits, not the range of the ground motion that they sample. That becomes one of the difficulties here. What do you get? So because of that, the resulting set of models are not a mutually exclusive, collectively exhaustive estimate of what the ground motion is. Okay. We also create new models that haven't been published. I think we're beyond worrying about that, but that has been an issue before, because you start to generate new ones that are spanning the space, and you now have a model where there is no pedigree of a peer-reviewed publication, other than the peer-reviewed publications were used to generate that thing. So we went to, PEGASOS was going on at about the same time. For that, it was a SHAC Level 4 study. Here, this was following Yucca Mtn. The idea was, look, if the experts are going to use weights on GMPEs to get to their evaluations anyway, let's have them just give us those and focus on that rather than focusing on the resulting ground motion. Okay, so we just acknowledged that and said, tell us your weight. All right, so we would say, what are the weights on the GMPEs? And they could set a magnitude, distance, and frequency range for which the weights applied. So a model didn't have to have the same weight at all cases. So looking over a range of magnitudes, distances, and frequencies, and then we could divide that up into small pieces. And you could say, from 0 to 20 kilometers, use these models. From 20 to 50, use these weights, and so forth. So the answer, again, is a vector, right? You're giving weights on a vector, not a single ground motion value. And we get magnitude, frequency dependent weights for the GMPEs and the point source models that were arrived. So again, we're no longer sampling discrete distribution, right? We're no longer discretizing a continuous distribution. We're back to really relative merits of the models. And this was a struggle for people involved. So Frank Schierbaum was involved in this, and he really didn't like it. He wanted these weights to be mutually exclusive, collectively exhaustive descriptions of what the problem was. Okay. So the PEGASOS results use something like this. This is weights on GMPEs is like what is traditionally done. The only difference is the weights were allowed to change in magnitude and distance ranges. Because of that, we would have some cases where if my weights were changing from across a boundary, some of my fractals would jump and so forth as I get a non-smooth evaluation to that whole thing. So in BCHYDRO, we did a SHAC Level 3, and so having seen all of this, we were trying to find another way to do the problem. So we moved to the scale backbone approach for the subduction earthquakes. We did use a standard sort of weights on GMPEs for crustal earthquakes in that area. So our question is, what are the weights on these GMPEs for the subduction? It's, again, we're answering now weights on a vector, right? Because our answer is no longer a single ground motion value, but it's the ground motions for a whole range of magnitudes, distances, and frequencies. We selected a backbone GMPE. Okay. Then we created a suite of scaled versions of that, up and down. The uncertainty factor was not the same everywhere, so the scaling maybe was broader at the large magnitudes, above magnitude 8.5. We had more uncertainty, so we let it go up, broader ranges, but things were scaling up and down. So because of that, now we can think of these as statistical weights on the scaled models. And if I say my space of solutions is all captured by this one model and how I can scale it up and down, I'm back to discretizing a continuous distribution, and I can think of this as mutually exclusive, collectively exhaustive estimates of what the ground motion is. It doesn't address changes in the magnitude and distance scaling, though. Okay, that's been a problem here. So this is just from BCHYDRO. We could have had suites of GMPEs here, but I have a backbone model, and I'm just going to scale it up and down. Okay, so I can create a suite of those, and I can think of that factor being something that I'm just going to have my now distribution on, and it's a straightforward interpretation of the weights as probabilities. Okay, so we're back to that, which is what we really want to be doing, getting the weights back to probability space. So the advantages of this, so scale backbone approach was I think, something that coming out of PEGASOS we thought really would make our life a lot simpler, because we could go back to models being mutually exclusive, models being collectively exhaustive in terms of the ground motion level. They're not collectively exhaustive in terms of changing the magnitude or distance slopes, the details within that. And now we can treat these weights as probabilities again. They're back to what we want the logic tree weights to represent. It doesn't capture uncertainties in the scaling, again, magnitude and distance, tends to lead to overestimation of the fractals because we have full correlation. So the thing is entirely high or entirely low, okay, whereas really I might have a steepening distance slope, so it's high at short distances and low at long distances and so forth. Same problem of creating a bunch of models that were not published before. Okay. So in SWUS, what are we doing, and what is Nico going to describe for you is simply the next evolution of this thing. And so it should make sense. So instead of, our concept here is to develop a suite of representative GMPEs that span the full range of models, capturing changes in magnitude and distance scaling, not just moving things up and down by a constant. We have a mutually exclusive and collectively exhaustive set of models when we look at them in the Salmon's map space. Okay? So we're going to start, so we basically have a question, what are our GMPEs and what are their weights? Okay? We're answering, it's a vector, so we need to deal with the vector, magnitude and distance. We're doing that separately for each frequency. Okay? It would be nice to do them all at once. That's coming a few years down the line, but we're doing them now a vector one at a time. The weights are statistical weights for the GMPEs. It's simply discretizing a continuous distribution. Because we're working with a vector, though, of ground motion, magnitude, and distances, how do you discretize that whole thing? And the Salmon's map is taking that and just collapsing it into 2D so we can work on a 2D space and discretize the distribution in 2D. That's all that's happening. So the concept really is the same thing that we've been doing all along. Okay? The difficulty is there's a large number of GMPs that is coming out of this, and we're going to have to either just make ourselves more efficient so we can run them, or be more clever about the whole thing, or downsample the size to a more manageable number. Okay. Right now we're also running independent for each frequency, so we're not capturing the correlation across frequency. That can be addressed, but that's another year down the line before we're going to get to that piece of the problem. So in SWUS, what are we talking about? And if you think of before, we were just taking a ground motion and discretizing that distribution in 1D. We're just taking that. We've taken our vector of a lot of magnitude and distance combinations, and we've flattened it out or projected it onto a 2D plane on these Salmon's maps. And this is showing the space that we think are technically defensible solutions, shown in red. And each one of these points has an area drawn around it, and it's representing that area of the Salmon's map. We're trying to now simply get weights, like we're discretizing this distribution, to discretize this 2D distribution. Right? This space should be all of the models. All of the ground motion models are in there now, so we're getting magnitude scaling changes, distance scaling changes, constant scaling changes are all brought in there. Okay. That's all this is, right? It really should seem very simple at this point. Okay? So Nico's going to explain all the details on how this happens, but conceptually this is no different than what we've been trying to do all along. Have a complete distribution of the problem, a set of mutually exclusive, collectively exhaustive models, and weights that we assign to them that are truly probabilities. Right? That's what we've been after, and that's what this lets us do. So it's really exciting that we've gotten all the way to make this thing work, and Nico's going to show you how we've gotten to the point of how do you get the weights within these things. Right? That's the next trick. It's moving forward. If I summarize all of this, we're trying to do, our goal is to find weights on models that we can treat as probabilities, and that we are simply downsizing or discretizing a full distribution to get a small set that we can run that's manageable. Our goal is to have them mutually exclusive, collectively exhaustive, right, in this whole treatment. Early on, that's what we were doing, but we were doing it one point at a time as a scalar, and how you put that all together made the whole problem more difficult, okay, because it's really, the whole ground motion model needs to be brought together. EPRI brought in part of that within clusters, but had the merit weights for the clusters themselves, so it wasn't quite getting the whole problem. PEGASOS went to merit weights on the GMPEs themselves. BCHYDRO did this, got a, I wrote that wrong. Mutually, that's not good. It should be MECE, but ignoring the correlation on magnitude and scaling. I mean, the scale backbone approach is conceptually easy, but it's not picking up all of the suites of models. Hanford, I think what they're doing, you guys correct me, is we've added a magnitude scaling term in there, so the magnitude differences are there, but the distance scaling has not been incorporated. So it's moving in the same direction, and all we're doing here is that same idea of what's going on in Hanford, adding into it the distance scaling term and doing the discretization of the process in the Sammons map. So the Sammons map gives us a framework for taking this higher dimensional vector of all the magnitude and distance pairs and collapsing it into 2D so we can draw a 2D space and think about it in a way that is easily understandable. Okay? Clear to everybody? John. He needs a microphone. Yeah.
John Stewart. So I'm not familiar previously with the scaled backbone approach. Are you adopting a GMPE from a library and then
we pick a good one, okay, one that's well behaved, and then we in the simplest approach in BCHYDRO, think about, you just multiply it up and down by constant.
To achieve the percentiles that you're
right.
looking for.
Right. So you could say, all right, the whole thing is 20% higher at all distances and magnitudes, or 20% lower, or 50% higher, and you just put a weight on the scale factor that you're going to apply to it. That way you cover all the ground motions. They're there, and it meets your mutually exclusive, collectively exhaustive, but it's missing other features of the ground motion models because it's just one of them scaled up and down. Right. So Hanford took that approach, but then added alternative versions of the magnitude scaling to that. Okay, so then they have sort of a suite of scaled backbones, if you want to think of it that way.
Okay. And with the model that we'll talk about in just a moment with Nico, I think we get the idea that there's a space that's collapsed down to 2 dimensions, and then we can visualize them there. Be good in that next meeting to conceptualize how many dimensions is that space that's being collapsed into 2D?
I think it's 175,
yeah.
something
okay.
like that. It's every magnitude and distance pair that you're going to put in there.
And frequency?
And frequency, but we're doing frequency one at a time, but if we put all the frequencies in there, that would be there. Nico will go through all of those details. All I want you to do is to not be sitting here thinking, what's going on? This is all wild. It's not. It's really a simple structure to get us back to what we've been trying to do all along. Right? Get the weights to represent probabilities that is discretizing a continuous set of models that we have all of the models captured. Nothing more than that. Okay, are you ready for Nico now? We have several hours. Okay, everyone should be rested. We want to do this in the morning. So you understand how this is happening. But pay attention, think about in the end, how are we going to get the weights for these little zones, right? And what are we going to be doing? So he's going to talk about some alternative ways that we can get at that, and that's really where the subjective judgment comes in. What data sets, what approaches do you use to determine the weights? But that's like saying once you have those, then the selection of them is really a statistical process that's straightforward. Okay? Ralph.
Ralph Archuleta. Do the areas in this reflect basically the overall, let's say, spread in the 170 dimensions? I mean, they're going to project onto this two-dimensional space, but the areas are different. That each of these those look like Baroni cells. So.
Yeah. So the areas. I don't want to go too far into this. This just means that this GMPE is going to cover this much of the space, right? We could have split it into two, but then we have more. And our goal will really be to see if we can collapse some of these two together and say they're similar enough by doing some hazard sensitivity so that we can limit it. But this is what we're starting with, somewhere on the order of the 30 different regions in those models. So I'll let Nico go through all the details. I just want you to be thinking conceptually what we're talking about is a pretty straightforward process that's similar to what we've been doing 20 years ago, right? In one dimension. We're just trying to now do it in a higher dimension space. All right. While Nico is talking, I encourage you to interrupt him, okay? So there's plenty of time for discussion, and so we don't want him to go on and have people get lost. So Nico's very good and patient at explaining things. So, let's see. Can you get that? I think you can do that.
All right. So I'm just basically going to go through the details of what Norm just said. So this was all done for SWUS. So it's Western U.S., and it's all in periods, not in frequencies, because we're still dealing with the response spectrum. The SWUS TI team played a major role, but also PPRP, like Ken and Brian, played a major role in this. Right, and I'll just start. Just in case you're not familiar with SHAC, we want to capture the center, body, and range of technically defensible interpretations. And in this case, I'm always going to talk about median ground motion. So we want to capture the center, body, and range of median ground motions. And this is difficult with just a discrete set of GMPEs, because they're just discrete, and the things that Norm just described, they're not mutually exclusive, collectively exhaustive. But ground motion is essentially continuous. If you remember the plot from yesterday where we had this uncertainty and magnitude scaling, that's a continuous distribution. It's just a sample from the uncertainty distribution of the coefficient. So basically, it's much easier to assess the center, body, and range using a continuous distribution of models than using some discrete set of models. So that's the basic thing that we're going to do. We're just going to take a set of GMPEs and then estimate a continuous distribution out of it. And to assess then the models and to assess where do we need to go, we're just using those visualization tools that Norm just described. So, okay, basically Norm just said that. If you just select some GMPEs, put weights on it, they're not mutually exclusive, collectively exhaustive, so you run into all these problems on the logic tree. You can't interpret the weights as probabilities. The models might not be independent, which creates a further problem. And if you just scale it up and down, you miss uncertainty in a magnitude and distance scaling. We want to address all of that, and how we're going to do that is we just say a GMPE, a published GMPE is a point in a model space. So we have some abstract model space, whatever that is, and a published GMPE is just a point in there. But this model space covers all possible GMPs, so it covers all the models that are not published. So you can think of it that there are unpublished models which are just, nobody has published them. So for example, if you think about the NGA project, you had 5 developer teams. If you had 10, you would have probably have 10 different models. So you would have a larger sample of that model space. So what we're going to do, or what we should do, is we should base the center, body, and range of the technically defensible interpretation based on all the models that are possible and not just the ones that are published. And to get to those unpublished models, we'll just make the assumption that the GMPEs is sampled from a distribution of models. So you can think of it as a GMP developer is just a sample from a suite of all possible GMP developers. You know, we have all these people in the room, and we just sample randomly 5 out of them, ask them to make a GMPE. If we ask all of them, we have a larger space to work with. Okay. So that's just the basic assumption that we're making, that the GMPE is a sample from a distribution of a model, and then all we have to do is we have to estimate this distribution. Okay. So if we think about it, a GMPE is just a sample from some distribution. And this distribution, well, I should say that I'm going to take, whenever I say about, say, GMPE, I take equation literally. So GMPE always means median prediction in this presentation. So this distribution of GMPEs can be thought of as the distribution of physically plausible functions. So it's the distribution of functions which increase monotonically with magnitude, decrease monotonically with distance, have certain BS30 scaling but are not too steep, and so on. So just all the functions that are physically plausible, and we have a distribution over them. That's actually kind of a complex distribution if you think of it. There are a lot of knobs you could turn for a GMP, but we can simplify that in a great way if we just assume that each GMPE has the same functional form. If each GMPE has the same functional form, then this complex distribution just reduces to a distribution over coefficients. So each GMPE then has the same set of coefficients, let it be 10, and then we just have a multivariate distribution over the set of coefficients. And then this defines the space of the GMPEs that we have. That's pretty much the same thing as was shown yesterday with this uncertainty distribution. That's just the distribution over the coefficients that Justin estimated for that GMPE. And so if we do that, then all we need to do is we need to estimate this multivariate distribution. And in this case, we're making a further assumption, which is a pretty strong assumption, that these coefficients, I'll call them theta, so these are the parameters or the coefficients of the common functional form, are sampled from a multivariate normal distribution. So then all we have to do is we have to estimate the mean and the covariance of this multivariate normal distribution, which is nothing else than the well, you could actually do that while you estimate the GMPE, estimate this. What's usually published is the mean, but not the covariance. So we're just taking published models and trying to estimate this covariance from the end. Okay. The question is that justified? And I mean, a lot of GMPs usually have a different functional form, and a lot of work went into that. But on the other hand, they're all similar. They're all scale monotonically with magnitude, decrease monotonically with distance. The slope of the magnitude scaling can't be too large or cannot be too small. It's just a certain range that we have. And so basically, we can capture the essence of most functions with a simple or with a common functional form. On the other hand, for example, we don't need everything for all applications of a GMPE. I mean, a GMPE that's developed is developed to work well for all cases. But for example, in SWUS, that's a site-specific application. We don't care about the VS30 scaling for SWUS because all we need to do, all we need to have is ground motion prediction for proc size, so for VS30, 760 meters per second. We don't care. And the epistemic uncertainty in VS30 scaling just gets soaked up in the bias term, in the epistemic uncertainty of the bias term. It's just scaling it up and down. So we don't care if we capture that part. The same thing, we don't care for SWUS, or at least for Diablo Canyon, we don't care if we capture the long distance part. All sources are close by. So what we really need to worry about is that we capture that part. We don't need to worry that we capture ground motion generation at 200 kilometers with that common functional form. So therefore, it's a very strong assumption and it's a very strong simplification, but I believe it's justified. The same thing is, we're not doing this to generate ground motions per se. In the end, we're integrating over the magnitudes and distances. So if you have a function that captures the essence, that has on average mean residual to the original GMP, and if we're integrating over it, we're integrating over all the positive and negative residuals. So we're actually integrating out the errors that we make. All right. So basically, how do we get to this common functional form and from that to the GMP distribution is that we just select a common functional form. Then for each selected GMPE, we generate synthetic data. We just generate data at certain magnitudes, distances, and in this case, Style of faultings and Z-Tor values. And then we just fit. We fit the common functional form to those synthetic data points. And then we have a set of coefficients, theta I, for each ith GMPE. And from those sets of coefficients, we can calculate the mean and the covariance. And then given the mean and the covariance, we can just sample new model. We can either work with that directly. It's a nice multivariate normal distribution, which has a nice PDF. Or we can just sample new models and then work with those sampled models. And that's basically what we're going to do in the end. All right. So the overall approach is we take some selected GMPs, so we take good ones. We fit them to a common functional form, estimate the joint parameter or coefficient distribution, and then we generate new models. So we sample from this joint distribution, and then we have a really large distribution or large set of models, which are all mutually exclusive and collectively exhaustive. But they're too large. The range that we have is too large because we're sampling everything. And then we need to evaluate those sampled models with respect to the application. And therefore, we're going to use those visualization tools. So in the end, we want to reduce the model space. Okay. So this is all done for SWUS. So that's estimating the hazard for Diablo Canyon and also for Palo Verde nuclear power plant. I'm just going to talk about Diablo Canyon here. As I said before, the output is hazard for rock. So we don't care about VS30 200 meters per second. We only care about 760. The controlling sources are nearby faults, and they're all nearby strike, slip, and reverse events. So we also, in this for Diablo Canyon, we don't care about the normal faulting factor of the GMPs. Okay. So this is it. We just care about the part close by, strike slip reverse, and VS30 760. Okay. So there are 8 GMPs selected for that, which are based on some quality criteria, which is the 5 NGA models, plus plus the Yucca et al. From that's actually 2014, which is based on European data. And then there are 2 Japanese models, Zhao et al. 2006 and Zhao and Liu 2011, which is basically the Zhao et al. 2006 model, but with a constant magnitude scaling for large magnitudes, with a constant ground motion for large magnitudes. And then we're just going to generate synthetic data for those from magnitudes 5 to 8, because that's the range we care about, for distances 1 to 70 kilometers. Actually, in the end, I included one point at 200 kilometers, just to make sure that it doesn't really go bad at long distances. And then we're all generating this for the footwall, so it's very easy to calculate the rupture distances from RGB. We use different values of ZTOR and the hypocentral depth for each magnitude, just to get also to get an estimate of the depth scaling, because a lot of 3 of the NGA models have a depth scaling term in there, and so we also want to capture. And then we're doing this separately for 17 response spectral periods between 0.01 second and 3 seconds. All right. Yes. You need a microphone. I can't hear you.
Why didn't you go to 10 seconds?
Because the European and the Japanese models are not good for 10 seconds.
So
they are only valid up to 3 seconds.
Okay, so the seed GMPs should have a minimum requirement of your application.
So
okay.
we can't estimate the distribution for 10 seconds from a model that's not good for 10 seconds.
Nico, when you said you generated synthetic, this is Ralph Archuleta.
Right.
When you generate synthetic data, are you generating it now with the common functional form, or are you using specifically these?
No, we're using these GMPs, and for each of those GMPs, we generate median predictions for those cases. Okay. And then we're fitting the common functional form to those median predictions. Great. Fast. So this is the common functional form that is selected. Theta are the parameters. They're in total 10 parameters. And so what we see is, so this is like a constant term. This describes the magnitude scaling. And here this describes the distance scaling, as well as, where's the other term here? We have the inelastic attenuation. We have a depth scaling term in there. And this describes the scaling with reverse faulting and strike slip. So F is 1 for reverse faulting events, and it's 0 for strike slip faulting events. And basically what we see is we have this term here, which is common to almost, I think it's common actually to all GMPEs. So all GMPEs have this type of depth scaling in them. Some have some additional terms, but basically this describes the depth scaling of almost all GMPEs. Distance scaling, right. At least most of the NGA models have some sort of trilinear scaling, magnitude scaling in them. They have different breakpoints, but most of them have some sort of trilinear magnitude scaling in them. And that's the same thing that we're using here. And then we have additional just linear depth scaling based on ZTOR, and just this constant term for reverse faulting events. And then
what happened to hanging wall? Because especially for Diablo Canyon.
Well, we're fitting all of this. I'm not going to talk about the hanging. We're fitting all of this to the footwall, and the reason is that it's difficult to find a common hanging wall factor for all of the models. The additional difficulty is, so basically the thing is we have two Joyner-Boer distance models which have an implicit hanging wall, but it's difficult to fit the Joyner-Boer models to a hanging wall term, which is then valid for rupture distance, for example. The other thing is we have the EPRI model doesn't have a hanging wall term. The same is with the two Japanese models, even though they are based on rupture distance. So that's why we're working on the footwall, but then we have an additional hanging wall model that is then in the end added to the selected models. That's
the hanging wall model. So there's basically two branches to our logic tree. The models that are the strike slip and footwall based models, and then there's going to be hanging wall effects in a suite of hanging wall models that are also done in a consistent way so that we're sampling the full range that are applied to those. But here we're focusing, especially for the East, the concept that he's trying to get here is what we want to get. How do you take models and create a full space of models and then sample them with weights that are probabilities?
right. So basically the hanging wall factor comes after everything I'm talking about. So I'm not going to talk about that at all. So the thing is, so we're going to make some error with this functional form when we fit that to the GMPEs. And this is actually shown here. And this looks really bad, actually. So this is, the left are residuals for the ASK14 models, and the right one are residuals for the Yucca et al. 14 model. So left one of the NGA models, right one the European model, but the main difference is that the ASK14 is a rupture distance model, and the Yucca et al. Is a Joyner-Boer distance model. So if we're fitting everything to rupture distance, we get these blue residuals. They're really, really small for the Abrahamson et al. Model, and we just have here this kink, which comes from the fact that the ASK14 model has a magnitude breakpoint at 6.75. We have it at 6.5, so we're just making this error there. So we're not capturing that exact breakpoint. But on the other hand, it's pretty good. The same thing here. If we're fitting the Yucca et al. Model to Joyner-Boer distance, we get pretty much the same thing. The residuals are really, really small. We're just making some error at the breakpoint that the Yucca et al. Model has. If we're If we're fitting everything to the wrong distance metric, so to the distance metric that wasn't used, we have much larger residuals. And the reason is that we're using different Z12 values per magnitude. If you think about it, we're all on the footwall. If we have the same magnitude but different Z12 values, then the Joyner-Boer distance will be the same, but for those different Z12 values. But the rupture distance will be different. So therefore, for the Joyner-Boer model, we will generate the same ground motions, but when we're fitting it to rupture distance, we have the same ground motions, but in a different distance. So therefore, we're going to make an error. And the same the other way around, if we're just fitting everything to Joyner-Boer distance.
One question, Nico?
Yes.
Yeah, you're showing us that the mean residuals are reasonably well behaved. What about the standard deviation in each one of those clouds of points? How large is it?
That's pretty large. So if we're fitting the ASK14 model to rupture distance, the standard deviation is really small. If we're fitting it to Joyner-Boer distance, it's pretty large. Yeah, that's actually, we can actually get that down. So we can actually get an almost perfect fit if we include the Z12-dependent fictitious steps. But that basically means that we are correcting for rupture distance or correcting for Joyner-Boer distance. So that basically means that we're not fitting them to rupture distance, but we're still fitting to Joyner-Boer distance. And then we have a parameter that's either 1 or 0, and that messes up the correlation. That's why we didn't go into that direction. But basically, you're right. It is pretty large, but on the mean residual is pretty well behaved. So if we're integrating over that, we're integrating over all of this, and we're integrating over the positive and negative values for hazard, it doesn't matter a lot. Now I forgot to include those plots there, actually. But
okay, one way you'll get to sort of see the impacts of all of this is comparing the suites of models that are generated to the original ones in their magnitude and distance scaling. So you'll see, I mean, the idea is we should be capturing them, right, and that these models are there. So that's part of the check of the process at the end.
Or can you go all the way to hazard?
All the way to hazard is the better place to check it. We haven't done that yet. Can you go back one? So, okay,
John,
go ahead.
So my question is, I'm trying to make sure I understand where the red dots are coming from on the left figure and the blue dots on the right. So is the red dots on the left generated by the ASK model you randomly sample?
no, so that's basically when we have our synthetic data for different magnitudes. We have the synthetic data for magnitudes 5 to 8, and then in a suite of different distances, and the Tor values, and also strike slip and reverse faulting events. So and then we're just fitting that to the common functional form, and then we take the residuals of that fit. So it's basically, so if you think of this as the data, just as if you're fitting the GMPE, you have a suite or sets of data, and then you're fitting it, and then you're plotting the residuals against magnitude and distance.
John, this is the misfit from imposing a common form onto your model or to Joseph's or my model, right? It's not going to be identical. So how much what's the inability of the common form to match your model exactly? That's what those residuals are showing.
Right. So the data that's being fit is model generated in a way.
Yes.
Right? Yeah. Okay.
Yeah. There's no observations here. It's all
right. So that's why I always call it data, and not it's not synthetic data. So
pseudo data or something.
Yeah.
Okay.
Right.
And just one quick comment, Nico. Again, I encourage you to add error bars or whatever to show that range of uncertainty. So we know exactly what the price we're paying with the functional form.
So, Gabe, did you mean standard deviation of the mean?
Right.
Yeah, exactly. Standard deviation of the mean, error bar kind of thing. And that way you know, again, because this class of points depends very much on how many points you sample.
Yes.
I think that will obviate the last 5 minutes of questions.
Okay. So you need a microphone. You need a microphone.
But it doesn't change the basic statement is that if you're fitting the common rupture form to ASK, you get the blue points, and there's almost no scatter. The blue points have no scatter in them. The red points are fitting when you try to fit the ASK rupture predictions with a Joyner-Boer model. So that's the scatter from trying to fit a functional form that was not used in the model.
So can I suggest next time you present this, you do something Norm hates is animation. You just plot the blue points on a model that is with our RUP and the red points on a model that is with RGB, and then you put the clouds the
right. So basically,
people will see.
as I understand it, Nico.
Yes.
As I understand it, there are as many blue points on the left plot as there are red points. They're all collapsed into one point.
Right.
They have 0 standard deviation.
Right. No. All right. No, I mean, even if you do that, I mean, if I could plot them from minus 0.05 to plus 0.05, but you still won't see the scatter in this cloud. So this cloud, this small cloud there is the same number of points as this red cloud.
But people are thinking that the blue point is the mean of the red.
No,
and it's not.
that's not. No.
So no, Nico, all you need to do is put a little offset between the red points and the blue points. And the blue points are the mean and standard error, and the red points are right next to it, and that will, I think, improve it without
Okay, now I understand the confusion, right? So no, it's not. This is two different fits. These are the residuals of two different fits.
Nico, just to understand. So if you use RROP for ASK 14, still you are going to have some misfit because
it's
the function of
right. So it's just the main misfit comes from just this different breakpoint that we have. If I use 6.75, this would be flat.
Exactly.
We would just, if you're looking at this on the left, if you fit an RREP model, there's less than 5% error between the common form and the form we used, and it's generated by having different breakpoints where there's kinks, right, because you can't capture the kinks. If you try to impose an RJB form, it's not going to work in close particularly, and that's what they're driving up the variability, and the same on the other side. Is that clear to everybody what's there?
But actually, you get a much better fit if you don't have depth scaling in there, because if you don't have depth scaling in there, because then you only have one RGB value per magnitude, and which has the same ground motion, and that gives a much better fit if I fit then the rupture distance model to RGB or the other way around. Okay, to accommodate this difference, we fitted both all the models to both rupture distance and RGB distance, and there were a couple of reasons for that. Basically, they behave differently on the hanging wall, and at first we thought we'd just go directly to the hanging wall and then capture the characteristics of both types. We also reduced the misfit, so basically we have one distribution that kept one set of coefficients fitted to RUP that captures the RUP models pretty well. We have one set of coefficients fitted to RJB that fits the RJB models pretty well. So overall, we're reducing the misfit. So we just did that, and we fitted everything, but in the end, the TI team decided to give 0 weights to the RGB models, overall to the generated RGB models, not to the original RGB models. So they're still in this distribution. So basically what we get is we fit all of those models to the common functional form using both RUP and RGB. And that gives us two different sets of coefficients, one that go with RGB and one that go with RUP. And then we calculate for both of those sets of coefficients, or sets of coefficients, we calculate the mean and the covariance. And that gives us two different GMPE distributions. Okay. So basically, this is just the whole approach shown graphically. We have 8 GMPEs, generate data for them. So basically, we generate data at a couple of magnitudes and distance values. Then we fit them with a common functional form. This shows the fit to RUP, and here we see we have some misfit, which is actually in this case due to the RGB models, that we're not capturing them in close. But then once we fit them to the common functional form, we calculate the mean of the covariance distribution, and then we just sample. We just sample new sets of coefficients, and for each of the new sets of coefficients, we just calculate new ground motion data. And this is shown here. So in this case, this is 1,000 newly generated models plotted against magnitude and distance. And what we see is we're capturing the full space. We're capturing both the space in between the models. So here we're both interpolating, but we're also going outside of the range of the original GMPEs. That means we have a much larger space of GMPEs to work with now to capture the center, body, and range of the TDI. And that was the main idea.
Nico, when you go outside the range, there should be some judgmental limit that
right.
Otherwise it's outside the whole database.
That's true, and that's basically we need to evaluate the space.
Okay.
That's right. That's then the whole idea of the visualization, that to evaluating this new set of models.
One quick question, Nico. Sorry. Did you remove any non-physical, non-monotonic?
Yes.
Okay.
Yes, right. So in this case, we sampled new models, but there was the small probability that we get oversaturation, and we discarded those models that have oversaturation. And we discarded those models that have an increasing slope of magnitude scaling. So basically, you could sample a model that has not so steep slope here, and that gets steeper in this range. And we discarded those models as well. So we need to have a decreasing slope with distance, monotonically decreasing slope with magnitude.
Is that clear? You have to have curvature going that way, right?
This is Ken Campbell. This last assumption where you throw out models that oversaturate, and those of us involved in the Hanford project are aware that they specifically chose not to do that because they felt that it was required in order to get the appropriate distribution. Granted, I think all the models they eventually selected, none of them oversaturated, although Bob can speak to that maybe a little more. So this is a fundamental difference between the two. So I'm just curious why you chose to remove the oversaturated models at this point. Anyway, not necessarily in your final selection of your models. Or is that for the discussion? Sorry.
I think that's part of the discussion, but none of the models on which these were based allowed oversaturation, and so we simply imposed that same constraint. I think there's really nothing more to it than that. I agree you could let them through and then see what happens, but we were trying to, at this point, we stuck that constraint in.
And the Hanford result, the quote oversaturation resulted from imposing the epistemic uncertainty, which is larger at magnitude 8 than at magnitude 7, and imposing it symmetrically, and that forced some models the lower edge of that distribution to go down. And so it's basically occurring above magnitude about 7.5, and it's essentially coming from that additional epistemic uncertainty we added.
I think this is a question, but I know we're going to get to this as a different way to visualize this in a moment with Salmon's maps and everything else, but if we were to look, you have a high density of models, 1,000 models on the plots here. If we were to take a vertical slice at, say, 10-kilometer distance, what does the range of the median, the center body and range of the median, never mind.
Oh. Can you actually see the bars there? It looks pretty good on the screen here. So this is the slice through. Can you see this? So this is the slice through here. We're just cutting through here, and this is the range of the median predictions of those 1,000 models. And overimposed is in red the predictions of the original GMPEs, and then these other points are the original GMPEs plus minus the uncertainty model, the NGA uncertainty model from Linda and Borg. So that's plus minus 2 times sigma of the uncertainty model. And so we're capturing the original GMP predictions, but we're also capturing plus minus, if we just scale them, plus minus up and down, plus minus 2 sigma. So in red we have the original GMPEs. In cyan we have the original GMPEs minus 2 times the standard deviation of the NGA uncertainty model. And in magenta we have the NGA, the original model predictions plus 2 times the uncertainty model, or 2 times the sigma of the uncertainty model. So that's something like an up and down scaled version of the GMPs. And I just weighted them that I gave the median point 0.8 and the other point 0.1 and 0.1.
Nico,
yes.
Could you go back one slide? I thought I understood this, but now that you're talking there, I'm not sure. And I apologize. Maybe you could just go through this again. So I understand generating data for each GMPE.
Right.
Fit common functional
right.
form.
So and then we fit. And then this is the fit superimposed on that.
Right.
And then for each of those fits, we have 10 coefficients, right? So we have 10 coefficients times 8 models. And then we use some interpolated models as well. But then we have, 10 coefficients times 8 plus some interpolated models. And then from those 10 times the number of GMPEs that we have, we calculate the mean and the covariance of the coefficient distribution. It's just the multivariate normal distribution, and we sample new coefficients. But each of those new coefficients induces a new GMPE. So that's basically the same common functional form, just different values of the coefficients. And then we have a new GMPE. And then I just plotted thousands of those new GMPs.
Okay. Now I follow that. So you're sampling from that
right.
set that you've determined that you fit. Okay. Thank you.
All right.
I just want to be sure people understand the lower plot, the lower dots. So, remember when we had NGA-1 and the USGS added additional epistemic uncertainty? This is a calibrated version of that same concept, which is representing the statistical uncertainty of the model due to the limited data that was available. So that's sort of a minimum range that should have been imposed on each of the models. And he's just plotted it at plus or minus 2 sigmas, okay, and gone forward that way. Right, just to broaden out the range, right? So each model is broadened out up and down by a constant factor.
So this is similar to the scaled backbone. Right? Each of those is just scaled by 2 times sigma.
Can we go back to the previous one?
This one?
Yeah, it's encouraging to me that the range of the median models increases with magnitude. But it's also at a magnitude range where the original median models are tighter than, say, 5.5 or 6. So I like how it looks, but I'm just wondering why does it expand with larger magnitude? Why do you see that broader range at larger magnitude?
That range at magnitude 5.5 is because of the different
hinge points people used. Right.
There's a parameter space. Why is it broadening?
Well, we have a hinge point here, and then just the scale. So basically, this range here is determined by the marginal distribution or by the distribution of the coefficient that determines the magnitude scaling above 6.5. And that's just pretty large because in that range, actually, we have a pretty large range of different scalings of the model. So the EPRI model, for example, is pretty steep at large magnitudes, whereas some other models are not so steep. And this gets reflected in the distribution of that particular coefficient.
Yeah, could be the correlation is helping you get that effect because it's kind of preserving the slopes in the scale, the magnitude scaling slopes.
I don't understand the question. Sorry.
Okay, but if you don't, that's
No.
okay. I was trying to explain the answer to
I think you're wondering if the correlation of the high magnitude scaling and let's say the constant, right? It's a non-zero covariance term, may also be broadening that out.
Yeah, that was my question.
Yeah, because isn't it the basic reason, as I understand it, that it gets wider at larger magnitudes is the data is sparser?
No.
Well,
right,
I think,
and so that maps into the covariance, right?
But in the end,
it's generated, but because the data is sparse, the models are more variable, right?
So that's the underlying reason is that the data is sparser. That's why the models are more different, and then we're just capturing that the models are more different. The same thing that we showed yesterday, when we showed the magnitude scaling of the uncertain models, it also got wider for large magnitudes. That's the same thing.
So in the next slide, when you have the sigmas and you're scaling up and down, those are sigmas on the mean for that particular magnitude distance.
Yes.
Not sigmas like we normally think of sigmas.
No, so that's
not the aleatory sigma.
That's not the GMP, not the full aleatory distribution. Yeah. That's the epistemic uncertainty of the median prediction.
So if we happen to have a situation, going back to that previous line of discussion, where if it so happens that the models were artificially close together, even though the data was sparse for a particular condition, this procedure would not produce a large sigma. If the underlying models have a low variability, this would also have a low variability.
Yes.
We would have added this epistemic uncertainty to each one. Let's say there was consensus, so all the red points were on top of each other. Okay. We would then have, when he got his covariance, he would have got the same value with zero covariance or something. But when we imposed on top of it this width here, and then you would start to get a different. There may actually be a magnitude distance where the models all do lie on top of each other.
I think there is for magnitudes like 6.5 to 7 and close distances.
Yeah,
the NGA models are very, very similar.
Right.
So they all overlap for that particular magnitude distance range.
And so the only way we can start to capture that is to impose this additional, basically saying the models all could be scaled up or down. Right? But a lot of what he's doing is getting the mapping of how the range changes for different magnitudes and distances, right? That's going to go into his coefficient.
Okay, so what I haven't really talked about is, what I forgot is, because this is just a gray mess of lines, but all these 1,000 models actually have different magnitude distance scaling. So we're not just scaling up and down, they all have, so we capture some epistemic uncertainty in magnitude and distance scaling with these 1,000 models. And that's nice. So that's basically what we were after. Okay. Now,
going back to the oversaturation, and specifically our model allows formally oversaturation, but
in fact, whenever I've evaluated for any given magnitude or distance, there really never is any true oversaturation. Did you exclude our models on the basis that the magnitude scaling would allow oversaturation, or did you do it on the basis of whether, in fact, there was oversaturation when you plugged in
your model was not excluded, so your model is in there, but it's just when I sample new models, I don't allow for oversaturation.
Okay. Oh, I see.
So I don't allow for a negative coefficient for scaling above 6.5.
Okay, another question that maybe isn't appropriate at this time, but before I forget about it, isn't there a basic assumption in here that all these different models are independent and uncorrelated with one another? And, given the process that we all went through, that's hardly true at all.
It kind of is in there, yes.
But Nico has also non-NGA models.
I think in the end, Dave, you're right. There's a bunch of assumptions that Nico is making, but in the end, the process is working. That is, we're creating a broad enough range of models. In fact, they're broader than what we're going to say is allowed. So we're going to go back and trim it. And that's really the approach, is to fill in between and broaden the range, and then we can go chop out what's allowed. So you could probably argue with every one of his assumptions, and they're not precisely true, but they're close enough or reasonable enough that we're getting a good range of answers out at the end.
So you're saying the end justifies the means?
I'm saying the end justifies the assumptions that they are reasonable.
No, I understand. And is this going to be applied to the East? This whole workshop is for the East, I think,
yes,
isn't it?
This is what we're going to be doing.
And one of the reasons I mentioned that was that, if you go back to the older models, like 1997 SRL or some of the older ones, they're like geometrical spreading. Almost everybody assumed 1 over R, I think, except for Gail and myself. And that right there makes a huge difference in the predicted ground motions. And everybody's just following one another, and so they're very strongly correlated, and the results are very dependent on that assumption.
So again, yes, this is for the East. What we want to focus here and what we ask Nico to do is based on his SWUS experience. But I want everybody to ask questions and understand, but the details of a single GMP and those things might not be that big of a deal. By the way, I'm not talking specifically to you, Dave. But let's focus on the principles, and it's important also to understand those assumptions, but we're going to apply that to the East. So of course, we're going to have a larger distance range. We're probably not going to capture the style faulting and this and that. The principles are the same. That's really what I want everybody to understand here. We've not done it for the East. We're going to span the space with existing models, the new models that we're doing as part of NGA-East, and we're going to look at those, and then we might reject some models that are redundant as we span the space. If 10 models were based on one study, then we have to consider that. Okay.
I mean, if you think about the East, so basically what's coming out here is a suite of models based on different approaches. And then if we also capture the epistemic uncertainty of those models, so maybe either just capturing the standard errors of the coefficients or doing a posterior distribution over the coefficients for each of those, we already have a distribution of models. We might not take existing models, fit them to the common functional form, but we still need to evaluate those. Do they capture the same range and so on? Right. So that's all the next part of the talk, evaluation of a suite of models. And what will come out is a suite of models, right? So there will be a suite of models from the empirical Fourier amplitude spectrum model. There will be a suite of models from stochastic simulations. And then we need to evaluate those.
Right.
And that's
I'm wondering if we are jumping ahead of ourselves, because I think we are all thinking of how this could be used for the East, and everybody in the room is thinking a different thought. I mean, Dave was thinking the thought, but this wouldn't work for the East because we don't have those nice suites of GMPEs. And I'm sitting here thinking, oh, well, of course what we're going to do for the East is we're going to take this methodology, only we're talking about simulations rather than GMPEs, and maybe somebody's thinking something else. So maybe we all just have to take a step back and say, at the moment, all we're doing is absorbing a methodology. We're not talking about how this is going to be applied to the East.
That's correct, because we have different issues and different data sets, or we could treat simulations as a data set or as a GMP. So let's focus on understanding the methodology right now as it was applied, and after that, Nico has a set of issues for the East, are specific to the East. How are we going to apply that with the differences that the data has in our data space and our simulation space and the GMP space?
All right.
Slide 14 of 42.
Yes,
we have until 11 to go through everything, just to keep that in, but
right.
We have until 11 at least. Yeah.
So what we then did, in total, we sampled 15,000 new models, which was probably a bit too much, but so we sampled 7,500 from the rupture distance models and 7,500 from the Joyner-Boer distance models. And then we have these 15,000 models, but what do we do with those? We can't just give them all to Nick and ask him to run hazard. And they're also just capturing a way too large space. So we need to evaluate those with respect to the center, body, and range.
Can I interrupt again, just so it's clear to everyone? When he says 7,500 from RRUP distribution, that's the combined RRUP and RJB GMPEs all fit to a common form based on RRUP. So it's not separating the models themselves, it's the parameterization of them.
All right. So what we're going to do is we're going to use visualization tools just to plot them all on a map. And how that works is basically that a GMPE is nothing else but a function, or the median prediction of a GMPE is nothing else but a function. And if a function is sort of like an infinite dimensional vector. So it's a continuous thing with magnitude, and each of those continuous points would then generate an infinite dimensional vector. What we can do is we just discretize this function by evaluating it at certain magnitude and distance ranges. That's basically what we're doing, what everything on a computer is discrete. So what you're doing anyway, so when I'm plotting this GMPE against magnitude, I just evaluate it at a certain set of magnitudes, and just then the computer program draws the line through it. So then we discretize this function, this infinite dimensional vector, into a into a finite dimensional vector by evaluating it at certain magnitude and distance ranges. And then this gives us a point in a high dimensional space. So then each GMPE is a point in some high dimensional space, and the number of dimensions depends on the number of scenarios we use. And then what we're going to do is we're just projecting those points from this high dimensional ground motion space. So this is now, this space is a ground motion space. We're just projecting that down to 2D. And I don't know if this comes really out pretty well. So again, here we have 1,000 sampled models evaluated at magnitudes 5, 6, and 7. So that means each of those models now is a point in a 3-dimensional space. And I've plotted this 3-dimensional space here. And what we have is, so this axis is the prediction for magnitude 5. This axis is the prediction for magnitude 6. And this axis is the ground motion prediction for magnitude 7. And each of those points is one of those 1,000 models. And and the x coordinate of this point is its ground motion prediction for magnitude 5. The y coordinate is its ground motion prediction magnitude 6, and so on. And if I could rotate this thing, you would actually see that this is the plane. So even though we're in 3 dimensions, the points all lie on a plane. And the reason is that they can't be arbitrarily oriented in that space. it always must be that this coordinate must always be larger than this coordinate. This coordinate must always be larger than this coordinate. The same thing is, this coordinate can't be 100 times larger. There's some certain restriction of the magnitude scaling which is imposed by physics.
Nico?
Yes.
When you say, does it have to be a plane or a surface?
No, it doesn't have to be a plane, but in this case, it is pretty much a plane.
Okay.
So,
but it's not a cloud.
No, right. It's not. I mean, there's some sort of. It's not a perfect plane.
There is a thickness to it, so it's kind of planar cloud.
There's some sort of. There's a third dimension to this plane, but it's really small. But the basic idea is that we can just work in the 2 dimensions.
So it's not a cumulus, but it's a stratus, kind of.
Right.
Okay.
But you're right, it doesn't have to be a plane, so it could be, basically it's a 2-dimensional manifold in a 3-dimensional space in this case. And it could be a surface. And even if it's a surface, we could still project it down into 2D. Right. So now I hope I can get this to work. So basically, there are these 2 red points here. And if you think about this red point, this has a very, very low value for the ground motion prediction at magnitude 5.
Nico,
yes.
What happened to this then?
That comes back later.
Okay.
So the thing is, I can plot 3 dimensions.
That's fine.
If I add magnitude 8, I can, then I have 4 dimensions, and then I can't plot that anymore. But that comes later, just to show the concept. So
just to clarify again, your idea here is you're showing us 3 dimensions because we cannot see the thousands of dimensions.
But
That's
we can.
The idea. You can? Oh, Yusuf is good. He can. Okay.
But basically, what we can see that those models lie on a plane in 3 dimensions. So the basic idea is we don't work with 3 dimensions. We just work with the 2 dimensions. And then when we go to higher dimensions, if I add magnitude 8, I can't plot that anymore. But they still fall on a plane, and I just work on that plane instead of the whole point in 4 dimensions. So what we also have is, so this point here has a low magnitude, low ground motion for magnitude 5, but it has a pretty high ground motion for magnitude 6 and 7. So it's got a pretty steep magnitude scaling, whereas this point is high for magnitude 5, and it's low for magnitude 6. So yes.
I'm still confused about the plane. If they are on a plane, it implies there is a linear relationship between the 3 quantities, right?
Yes.
And there is here.
Actually, I don't think that it implies that.
You can always write a plane as an equation: ax plus by plus cz equals another constant.
Right. Yes.
That's a linear relationship for a plane.
But
a surface will be an arbitrary function.
Right. But I mean, that's just because we have a linear magnitude scaling, or like a linear with some kink in there.
But you have multiple models. Each model might be a plane, but all the models together will not be on a plane.
No, each model is a point.
Each model is a point.
Each model is a point.
Oh, all right. Okay.
Right.
I need to think about it. I'm sorry.
Right.
Nico, you've done all this at one distance.
Yes, right. So each of those.
One distance.
This is just, I think it's at 15 kilometers. So Rx at minus 15. But each of those, each model is a point. This is just the. This is the.
Whose phone is that keeps ringing every 5 minutes? I'm sorry. The fanfare? Really? Okay. Sorry.
Right. So this is just the prediction for one particular, this is the prediction for one particular scenario.
One distance, okay.
And this is the prediction for another scenario. And then I just plot that in this ground motion space. So this is also the thing, we're now working in ground motion space. We're not working in some other space, we're working in ground motion space. So this means two models which are close in the space have predictions that are close. But also the same thing is, if I put that on the plane, they're also close by on the plane. So that means two models which have very similar predictions for this magnitude 5, 6, and 7 are close in the three-dimensional space, but they're also close in the two-dimensional space when I just project this down. So this is how we can evaluate models which are close together in a high-dimensional space are also close together in the two-dimensional space. That's the basic idea. Okay, I hope the basic idea is clear, and then what we're just doing, instead of working in 3 dimensions, we're working in many more dimensions. So what we did is then we did just go from 3 dimensions, in this case 282 for Diablo Canyon. So we're just calculating model predictions at many different magnitude and distance scenarios. And those are from magnitude 5 to 8 and distances from 1 to 30 kilometers. Or our x values from -1 to -30. And then the first thing we do is we perform a principal component analysis.
Nico?
Yes.
182 per frequency?
Yes, right. So So this is all. Well, this is all old stuff. So we're still working with a period. Right. Everything is done separately for all of those 17 periods. Right. So at first we're doing a principal component analysis, and that's mainly just to make this comparable over frequencies. And that just gives us some sense of directions of the map. And then we're using the outcome of the PCA as the input to a Sammons map. And what the Sammons map does is it just minimizes the differences between the Euclidean distance of those points in high dimensions and the Euclidean distances of those points in 2 dimensions. So it tries to find a set of coordinates in 2 dimensions which have the same distance distribution as the points in high dimensions. So that means 2 points on the plane have the same Euclidean distance as the corresponding 2 points in the high dimensions. And the Euclidean distance is just there's a square missing. It's just the sum over the squared differences between the coordinates. And each coordinate in our case is a ground motion value, because we're working in ground motion space, in 182-dimensional ground motion space. Okay, so I don't think you can see that at all, but so these are the cases that we're using to visualize the models, magnitudes 5 to 8, distances 1 to 30 kilometers, faulting style 0 and 1, and in this case it's just an example for 0.01 seconds. And in red, again, we have the original GMPEs, magenta and cyan, plus minus uncertainty. And what we see is, so in this case, these models here belong together. And when we just add a constant scaling to each model, we're just going in one direction. We're just going up and down, but we're not going in the other direction. So we're not going into a direction which would correspond to a different magnitude or distance scale. what you should see, I don't think you can. There are 15,000 points behind this thing, which are outlined like this. And those are made up of the 7,500 sampled Joyner-Boer distance models and the 7,500 sampled rupture distance model. And they cover pretty much the same space. They actually cover the same space, which is good. So that means the distributions are pretty similar in the end, on the football at least. So I apologize that you can't see that, but the outline is about like this. So it's again, we're capturing a larger space on the map using the 15,000 models.
Nico?
Yes.
Originally, I thought there are 3, 5, 7.
1, 2, 3, 4, 5, 6, 7, 8.
Oh, where is the 8th one? Sorry, there is one of them.
1, 2, 3, 4, 5, 6.
Oh, that's
7,
the 6th
8.
one. Okay.
Okay. This is just to show that things work. This is the contour plot of the Euclidean distances in high dimensions to the center model. So that means we calculated the Euclidean distance in 182-dimensional space, and to the center model, which is somewhere there, to the model at 0 and 0, and then I just plotted the contours of that on the map. And the good thing is it's all circular. That means that the models, the Euclidean distances in 2 dimensions capture the Euclidean distances in high dimensions. Otherwise, if they didn't, it wouldn't be circular. Okay. That's nice.
So, Nico,
yes.
So that means that the measure of the error you're introducing by going from many dimensions to 2 is simply the little noise you see on the contours?
Right, yes.
Okay.
Right. So basically, okay, I haven't talked, but when you do a PCA, you can also, so you're just taking the first 2 principal components and plot them. That would already be a 2-dimensional map. And the amount of variance that you're capturing with the first 2 principal components is about 90%. So that's pretty good. So that means it's almost a plane. And everything, so the last 10% of the variance in these high-dimensional data cloud then comes from that it's not perfectly a plane, but there's some sort of third or fourth dimension to it. All right. So now we're working in ground motion space. So we've gone from model space to ground motion space, and that's basically, I mean, that's what we're interested in. We're interested in models that give similar predictions, or we are interested in models that don't give similar predictions to capture the center, body, and range of the median predictions. So basically what we can do is now we can just go on the map and say, what range of models do I want to capture? And where do I want to center? Do I want to center close to the GMPEs? Do I want to go somewhere else because I just don't trust the GMPEs? Or where do I want to go? But now we're working in ground motion space. So now we're working on a space which tells us how similar the ground motion predictions are of these 15,000 models. And that's the basic idea to do that. So now we need to evaluate those 15,000 models. And
okay, I think we're at a good breaking point.
Okay.
Would you agree? Maybe if you can leave the map of the ground motion space there, or you want to? Yeah. Okay. Where?
Yes. Let's just
okay.
2 slides away, I think.
Okay. Good.
Okay. So to evaluate the models, we have like different information available. We can just center on the mean of the GMPEs by saying, there's a lot of work going into the GMPEs. All the developers spend a lot of time developing them. They're all good models. Why should I go away from them? So I could just center on the GMPEs, try to capture like all the GMPEs, and be done with it. The same thing, we can try and collect data that is relevant for the application, and compare all the models to the data. And at the same thing, we can perform finite force simulations or other simulations, and then just compare the 15,000 models to those simulations. And this is basically all of those three things go then into the selection of a suitable and weighting of a suitable number of models. Okay, so this is the data. One problem with the data is that it's the data underlying norms model. So this is also the data that went into a lot of the models because it's the NGA data set. But this is all the data that we have for California. So we're just using the data set that was underlying the ESC14 model, using it on the football, just data on the football, Joyner-Boer distances smaller than 70 kilometers, magnitudes greater 5, and recordings per magnitude larger than 3, and corrected all the data to a VS30 of 760 meters per second. So this is the number of earthquakes, this is the number of records, and this is then the magnitude distance scattergram. And then for each of those for each of the data and each of the models, we can calculate residuals. We just calculated the residuals for all the 15,000 models to the, 600 records that we have, split those residuals into between event and within event residuals, but here using a fixed sigma. So we don't optimize for the standard deviations because we can accommodate a larger misfit with a larger sigma, and we don't want that. We're mainly interested in the median predictions and in the mean bias. So we mainly want to just look at the between event residuals. So therefore, we're using a fixed standard deviation or fixed values of phi and tau to split the residuals into between event and within event residuals, and we can also calculate the log likelihood of the coefficient. Or for each model, the log likelihood for the coefficients for each model. And this is how it looks like. So this is the histogram of the mean between event residual of the 15,000 models, and as well a histogram of the mean between event residual of the 8 original GMPEs. And here again, plus minus uncertainty. Now, the minus uncertainty is on the positive side because this is data minus predictions. So therefore, if we have minus uncertainty, we have larger predictions. That's right. And the same. And on the other hand, if we have larger, we have under prediction. And then we have the mean. The mean between event residual is about the mean bias of the models to the data.
So when the models are at 0, those are the ones that have a mean of 0 for this data set.
Right.
Okay? Centered on the data set that we chose.
And the reason that the GMPEs are on average well-centered, but this is just a subset of the NGA data set that they're just capturing much more. Some of them use a different subset. There are other modeling assumptions going into the GMPEs, so we don't really expect them to be exactly centered. but on average, they're pretty good. And then especially, we don't expect the Japanese and the European models to be centered. Right. And then we're just, this is the plot that Norm already showed, we're just making a contour plot on this two-dimensional space, using of the mean between event residual. And now we can actually see what's going on here. So we have the zero line is this one. So all these all models that are along this line are approximately zero-centered. And if we go in this direction, we have models that are either over-predicting or under-predicting, or no, it's under-predicting or over-predicting. And that's the same thing that we could already see with the uncertainty model. We're just in this range, we're just scaling the models up and down. Whereas in this range, we also have then some differences in magnitude and distance scaling. And then we're going to use this as the basis for selection and weighting.
Are the 15,000 models on there and we just can't see them on this plot?
So the 15,000 models are underlying this contour plot.
Okay.
Right. So this is this whole space is spanned by the 15,000 models. But if I just plot 15,000 gray points on there, then you can't see the contours anymore. So, right.
Let's stop right there because we'll come back to it. But let's take our break, 10 minutes, and start up again at 10 o'clock or so. And then we have one more hour to go through this, but just leave this one up there. Fundamentally, this is where we're going to say, if that whole space is generated by the 15,000 models, how do we subdivide it and then pick appropriate samples and assign weights to them? Because we're saying that whole thing is our full distribution, and we want to now discretize it.
Is there time for one quick question?
Yes.
Okay. What is the meaning, if any, of the shape of the region that is contoured?
Well, because the input is a PCA, this coordinate corresponds mainly to the first principal component of this high-dimensional space, and this corresponds to the second principal component. So in PCA, you're trying to, the first principal component is the direction in which the variance is largest. So that's why it's why it is this shape. But it basically means that there's more variability in terms of up and down scaling still in the models than in terms of differences in magnitude and distance scaling. Because these are, well, this is the main direction where we're just scaling up and down on average. This is all, I mean, this is also something, if two models are close in 2 dimensions, they give on average the same predictions over these 182 dimensions. So it still can be that they're larger at magnitude 5 and then smaller at magnitude 6, but that averages out. Because then and then you have another model that is smaller at magnitude 5. They can have the same distance and high dimensions. So basically, so if you go on this plot, and then so the first principal component would be the direction that maximizes, that has the largest variance, or the largest variance of these points. And then the second one would be the direction that has the second largest variance that maximizes the rest. And then the third one, it's not exactly a plane. So because then the third one would be really small, and then would just go like orthogonal. Right. Yes. Exactly. Yes. Right.
So we can actually visualize it.
Yes. Right. And it's actually, I mean, it's nice that it's actually that all these ground motion models are actually on a plane, or actually on a lower dimensional manifold. It doesn't really have to be a plane. It could be curved a little bit, but
I would like to think that's because there is some physics involved.
Yeah, right. I think it would go keep that's an original GMP. Yes. And then
the two about it are adjusted with bob and up
yes.
and down.
Up and right. Exactly. So that's just, it still represents 182 ground motion values. Each of those red points, and each of those points represents 182 ground motion values collapsed into two. But this one is just plus 2 times the signal, and then it's minus 2.
And then one more picture where you're showing the distribution. First of all, let me get this.
Yeah, this one. Okay. Yeah.
Well, I
it's
cyan and the other.
The beamer is actually really bad, but I should have. No. No, I should have. So this is the distribution of the mean bias. So I calculate the residuals of each of those 15,000 models to the data that we have. So that's the data underlying norms model. And then split the residuals into between event and within. The within are because we have the within are pretty much 0. So the mean within event residual is pretty much 0, and we only worry about the
Hello, group. Hello. Hello. Okay, everyone, we're going to start again. We have so many exciting discussions on epistemic uncertainty. Dave Boris, stop disrupting. We're starting. Rob Graves, that's enough? Oh, okay, the magic word is pay attention. Wow, that works. Norm really got something with that. Okay, we're going to start in just a second. Grab your coffee and come back. I know, it's always like that. Plus your introduction is very clear. Okay. Very good. And there's water there for you? Because I see sometimes you're just like... Okay, everyone. It's true now. We're starting again. So, Nico, let's start from the description of what we're looking at again briefly, just to put everybody in the right mindset for this map and carry on. We have about until 11 on this. And the rest is actually, did you put the NGA-East issues on this slide set? Or it's
I have
separate?
a last slide that's
okay.
Something we can discuss.
So then it means, so the way I organize this schedule is with a lot of fake presentations. Fake presentations, because basically we have until 11:30 on this whole topic. But that includes discussions and all that. So we're at slide 25 of 42, and we have to see how we're going to use that in NGA-East, and we'll propose an approach. But I think we're good. Okay.
All right. So just as a reminder from 10 minutes ago, this is the space that is covered by the 15,000 sample models. For each of those 15,000 sample models, we calculated the mean between event residuals to the data that we had, and just plotted it as a contour plot on this map. And then we have models that are over-predicting on this side, which are over-predicting on this side and under-predicting on this side. And here we have in red the original GMPEs, in cyan the GMPEs minus the uncertainty, and in magenta the GMPEs plus uncertainty, the uncertainty model. We didn't only calculate the residuals.
we also calculated the log likelihood. So that's log likelihood that comes out of the random effects regression with a fixed sigma. It's just running it through this one equation. And then we get this picture. So we get a pretty large plateau of models with a fairly high likelihood around here. And then it just breaks down. When we come to the edges of the space, we just, Norm called it the cliff ones. So we just, the likelihood falls off pretty quickly. And then the idea is that we can use both the likelihood and the residuals to select and weight models. So we want to have models that are consistent with the data. So that means they should have a not too large mean bias. They should have a fairly high likelihood. So we wouldn't select models up there or down here, for example. All right. In addition to data, there are finite fault simulations. So these are for several scenarios, for the Hosgri and the shoreline fault, if I remember correctly. And then these simulations are based on different scenarios. So they are simulated different magnitudes, from magnitudes 5.5 and 7.2, and also using different style of faulting. So for reverse faulting and strike slip. And we just selected them again, only the data, well, the simulations on the football. There are three methods: XSIM, Graves and Pitaka, and the SDSU from San Diego. And this is one example. So this is an example of the simulations versus distance. And the legend is not plotted, but in black we have the XSIM. In red, I believe it was Graves and Pitaka, and in blue we have SDSU. That's just for one scenario. And then we have the same simulations or the same three methods for just different scenarios, different magnitudes. And what we're going to do is we're just treating the simulations as an additional data set. We're just saying this is just data, and for each of our 15,000 models, we just calculate the mean, the residual to this data. And we're only calculating residuals, not the likelihood, because the variability of the simulations is not well calibrated. All right. This is the same thing as before, but now with residuals to the simulations. And again, we have the mean zero line is here, and our GMPEs are fairly well centered. In general, we have a very similar trend. We have under-predicting models over there, over-predicting models down there. But it's, when we compare that to the NGA data set, it's slightly different. So the contours are slightly different. So the information we get from the simulations is slightly different than the information that we get from the data. So it's just, overall, they're similar. It would be very bad if they weren't, but they're still slightly different. That's all that we can say, and then it was up to the TI team to decide how to treat the simulations versus the data, and so on.
Can you point out again where the zero line is on those two plots?
Zero line is, what the heck?
The
zero line is here.
That one.
And that one.
So it's to the zero has moved to the left on the simulations, is that right? Okay. Relative to the GMP.
Relative to the data.
What does that mean?
This is under prediction. So the original GPs under predict slightly. The on average the
simulation.
Okay. All right. And then, right, what we're going to do is we're going to use this map here. So this plot is used to select models, to select out of the 15,000 models, to select a suite of models that should cover the center, body, and range of the technically defensible interpretations. All right. And how that is done is the following. First, we are fitting an ellipse through the convex hull of all the GMPEs and the uncertainty model. So the convex hull is just the model, the outermost models. So basically, what we're doing, we're taking the model of what am I doing? We're taking from these 24 points. Yes, 24, because it's 3 times 8. We're taking the models that are the outermost models. And then we're fitting an ellipse through those models. Because we're fitting it, some of them will be inside, some of them will be outside, but on average we're fitting, the ellipse will capture this convex hull of these of all those models. Wrong way. I'm sorry. Okay. Then we're going to scale the ellipse by 1.5 and by 0.5. And because we're scaling it up, because some of the original GMPs plus minus uncertainty will be outside the ellipse, and we will also want to capture those. And then we're scaling it inside just to have a bit more of epistemic uncertainty closer to the center of the GMPs. Then we calculate the intersection of those 3 ellipses with certain contours. And these contours were chosen minus 0.3, minus 0.1, minus 0.15, 0, 0.15, and 0.3. So that's the range of bias that is allowed in the selected models. And then we select, that will give us a point on the map, and then we select the point underlying this map, which is closest to that particular point. I'm not exactly sure if I was clear.
So let's slow down here. So there's a judgment at this point. Right. We have that whole space to work with, right? Those are the 15,000 models. Having seen before the distribution of the likelihoods in particular, for this application, we could tell that things were going down tremendously at contours more than minus 0.3 or plus 0.3. So we thought that was a big enough bound, and we were already sort of throwing out parts of the model. In the East, we may have to be looking at a much broader range, because we had enough data from California to give us some tighter limits on what's going on. We could have done a bigger set, but then we would have more models with really low weights on the outside. So this was our first somewhat pragmatic attempt to limit the size of the area that we're looking through. So essentially stuff that starts to get further out than this, we begin to deem as zero-weighted models, or small enough weights that we can zero them out. Okay, so that's what he was doing. What you're seeing is a more sort of sampling in the Y direction here. You know, because the contours are going that way. That the Y direction is starting to pick up differences in magnitude and distance scaling. So we wanted to be sure we're getting a broad enough range. The mean residual is not very diagnostic about that part. You can have a lot of different slopes and still get the mean right. Okay, the likelihood starts to help you out on that piece there. But that was the idea of how we started to contour these, partly from feedback from Brian Cho and so forth, and going forward, saying, well, you really want to be sure you're capturing that part and not creating thousands of models. We're already trying to go down from 15,000 to something manageable. But that's what that first, let's call it even in slicing of the allowable space that we were going to consider. Is that making sense, what was done there? That will be different for the East, because I think we'll have a lot less constraints to work with. So we will probably be bringing through the broader range of models along with us. No questions on that? There's going to be a test on all of this.
Now, Nico, I see some points are not crossing contours.
The black points are always crossing contours.
Right.
So here.
Go down, right-hand side, more. Down, more.
Oh,
that's it.
That's probably because the way I did that, because the contours are not really extremely smooth. So what I actually did to get the intersection of the contours is that I went around the ellipse in 1 degree steps, calculated the some sort of smoothing out of the all of the models in the vicinity of each of those points, calculated the mean residual. Then I have a mean residual for each of those points on the ellipse, and then I selected those points which are closest, which have the lowest, which are closest to that particular contour that I wanted to match. And that's probably the reason why I'm not exactly falling on that point.
Nico, I have one more question too. And this kind of goes to Norm a little bit also. You indicated that your choice of plus or minus 0.3 was motivated by where you saw changes in the likelihood. The likelihood was really falling off beyond that. And in a way, is that really visualized here by how the contours are getting closer together as you move out from across?
You need to see the likelihood contours to see that.
You can't infer that from this. Okay.
Yeah, it's really hard to get that out of the mean residual.
Okay.
It's just different information.
Yeah, okay. Because that would obviously be a question then as far as sampling is that adequate to sample the range? What we're trying to get out of this is center, body, and range.
Right.
And the question is that plus or minus 0.3 big enough to capture the range that we're interested in?
And Nico didn't mention, but we had another constraint that if any of the GMPEs with their epistemic uncertainty, so if any of those points were wider than that, he went out at least that far. So let's say some of those points were the purple points were further to the left. Then he broadened out the contour to get that far. So we have to at least get the range of what's there in the GMPEs with the broadened uncertainty on top of them. It's a 2 sigma, right? Correct. John said, and that sigma is that additional certainty is at the 2 sigma level, right, of 2 times the epistemic uncertainty. So we could have gone further out and done more models. We just would have had a bunch of them that we would give very low weight to, and we'd probably remove them when we downsample anyway, because we want to get ourselves to manageable numbers of ground motion models, because the number of medians gets multiplied by the number of all the other pieces, and soon you're into thousands of models. So.
I think we did. So in the beginning, we did that. We didn't care about the contours at all. We just sampled those ellipses in 5 points per ellipse in equal angles. So just every 70 degrees, we just selected a point. And then it was said, we should focus more on closer to the 0 contour lines. And then it's just a question, how far do we go out?
So be sure you get close to the mic because your voice.
Yes, I'm really sorry about that. Okay, so this gives us then, in this case, I think 27 selected models. Well, that gives us 27 select points, and then we select the closest RGB model to that particular point, and the closest RUP model to that particular point. I'm only going to show, so in the next plot, I'm showing those 27 models, but only the RUP models. And that's because in the end, the RGB models were given 0 weight. And so here we see the original GMPEs, and we see, I don't know if you can see that, but I can.
Before you go on, because people are going to wonder, we gave 0 weight to the RGB models for this particular application because we're going to be on the hanging wall and having to deal with low dip angles, which RGB doesn't handle very well. At Palo Verde, that's not the case, but both models are brought along. And in the East, we may be looking at both of the models if it works, or we have to see if something, there's got to be a reason for it. So in this particular case, we're only going to be using the RUP models.
So again, to go back to the scheme, just to tie that back in, you're not rejecting original RGB models. You're rejecting the RGB parameterization of the 7500 you generated with this parameterization. So the RGB models are still in there because they span the space that you collected from.
They would have worked fine in this application just for strike slip and footwall. Okay, it's just for us when we tried to move them to the hanging wall in our particular cases or geometries, they wouldn't work as well. So his space is captured equally well. Can you go back to your contour? This big contour plot is spanned by both sets of models. It's not that the RGB models are on one side and the RUP are on the other.
That's the plot you could see.
Yeah, the plot we couldn't see had those two on there. So they're overlapping, really, and the idea being there's similar information involved in the model.
So, Nico, this is Ralph Archuleta. On the next plot, when you're showing that, what's causing that wide dispersion as you go between, let's say, 30 to 50 kilometers or 30 to 60? It's really broadening.
I don't know exactly why that is. That's probably because in some of the directions, we just have really, really big differences in those distance scaling models and the distance scaling coefficients.
I need to say my name. This is Norm. I think also when we're doing this on these maps, is only going out to, is it 70
yes.
or 30?
I'm actually going out. So on the maps, I'm only going out to 30 kilometers. So basically, all the information in the map is from 5 to 8 and from 1 to 30 kilometers. That's right.
So that other stuff, Ralph, is really not important for Diablo Canyon. If we were working on something and 50 kilometers was really important, the selection would have been refocused on that part of the model. Or if it had to work over a wider range, we could have done that. But our goal here is really everything, it's all within 20 kilometers that's there.
Right, so there's 182 dimensions were chosen to be working for Diablo Canyon. And it's actually, so for Palo Verde, we actually have 370 dimensions, I think.
And do you see that broadening when you did Palo Verde? Do you remember? Because I don't think that would happen.
Not as steep. No, it's not as
I think it's just it's the edge of the model space that we generated, right? And so then the constraints aren't as strong.
Because in that case, we're going out to 70 kilometers, so we're selecting models which are better behaved at 70 kilometers. All right. So so all of this was also Norm mentioned this in the this morning. So everything is done.
You need to speak out.
Okay, I need to. Okay, so everything is done for each of those 17 periods. Everything is done separately. So we're going through the whole process of estimating the coefficient distribution, sampling 15,000 new models, creating a map, calculating the residuals, the likelihood, and so on. We're doing this for all of those 17 periods separately, but then we're selecting for each based on each of the 17 maps that we have, we're selecting it in the same process. We're selecting models in the same process based on the same uncertainty ranges. And so that actually means, because the maps can be slightly different from period to period, that we also have can have a different number of models per period. And they don't, so the different models don't work together for different periods. So we don't get a smooth spectrum out of the models. And that's just one thing that's not required in this case, but this is something we should just keep in mind. Nevertheless, so this is just a plot for one particular model. So that's the model with the index 13. So that's the model on the middle ellipse, which has a mean bias of minus 0.12. And this is selected on all of them for all periods. And this is just the spectrum.
But if you did the mean model,
the mean model
period
would be
very smooth,
pretty
right?
smooth, yes.
Yeah.
But even though, I mean, if you think about, we're randomly sampling for each period separately models, and then just selecting them based on where they come up on a two-dimensional plot, based on a 182-dimensional space. I think it's fairly smooth. It's not something you will just, it's not smooth, but it's, for the selection process, it's still fairly smooth. Oh, the mean of the center model.
Can you repeat the question? Some people are misbehaving.
The question was, do I have the spectrum of the center model? And no.
The center, but the mean.
The mean.
I guess the center model is the mean, isn't, or pretty close.
It's not. It's pretty close to the mean. It's not always the mean, but I can generate that for you if you want. Okay. All right. So now that we have selected models on the order of between like 20 and 30, we need to weight them. So they capture range, but some of them are probably more appropriate than the others, so we don't want to weigh them just equally. Equal weighting is a bad thing. And so there are two things that were considered in weighting the models. The first one is models that are more consistent with the data should be weighted higher. So it means models that have a lower residuals should be weighted higher, and the same thing, models that have a higher likelihood should also be weighted higher.
Nico, one more thing.
Yes.
So from period 0.01 to 0.02, totally you get different GMPs?
Well, I mean, they still have the same functional form and everything,
right?
But they're not. They don't work necessarily together.
Not identical, but they should not be very different. I mean,
they're not very different if you look at this.
Yeah.
It's not something you would publish. You would just smooth it if you want to just work with a mean spectrum. But the hazard is calculated separately for each period.
Mm-hmm.
So, and imagine if you use just the normal GMPEs, you would. I think they did that in PEGASOS. You would weigh them differently for each period. So this also then just in the resulting distribution gives you some kink in that. So even though there's a lot of work going into into a smooth spectrum, if you just weigh them differently for each period, because you say this model is better at 1 second than it is at 0.5 seconds, then you you're essentially also throwing away that information that went into the GMPE.
So I think the bottom line here is right now we are not creating full GMPEs that work at all periods and saying here's now 50 different GMPEs and they're brought there every period. We're doing them one period at a time. Come back in another year and we may get the period thing worked out. Because what he's shown is it's not too far off when he takes all the models in the same area of the ellipse, but more work is needed on that. But for this project, we can just do them one period at a time. Or we're supposed to say one frequency at a time.
All right. So basically, now coming back to the weights, there are two, well, not really constraints, but two things that are considered. One thing is consistency with the data, and the other thing is, it's hard to put them, well, it's something like the information content of the model. So that basically means if a model is farther away, then it contains potentially more information. It's farther away from the other models, it contains potentially more information than two models which are really close. Because if you have two models which are really close together, so that means which give really similar ground motion values, ground motion predictions, you can probably just use only one of them. You don't need both. So even though they might both have a very, very low residual, because they're so close together, they contain basically the same information, and therefore you want to counterweigh those two different things.
Can I make one comment there? On the other hand, you might say that the fact that two models are together in some ways may suggest a strong prior, especially if they were developed independently and using different information. They came out to be together, you may think of them as a strong prior.
That's true, but we're not working on the published GMPEs anymore. We're working now on the samples from the GMPE distribution. So therefore, if some two models are close, give similar predictions, it just means they're really similar.
But those samples, again, the fact that if you have many models together from the original GMPEs, that's going to give you more density of points in that regional space.
Say that again, please.
If two models just happen to be identical because, even though let's assume they use different data. Right. That doesn't happen often, but let's assume they use different data, different thought processes. They came up with similar numbers. Then when you do your sampling, because you're sampling from those two models instead of just from one, you're going to get a higher density of points in your sample points. Yes. So I think the same idea carries.
Maybe if we took those 8 models and I stick one model in there another time, so I repeat it, and then I now generate my covariance matrix, it's going to be a little tighter, right? And that's what he's getting at. So there is some influence of that distribution of density of points. We're throwing that out for 2 of the approaches that we're going on. We're not using the density of points. So I think let's get to the way that we're evaluating the weights. One of the approaches says that density of points should be there, giving every model a pass-fail grade, and if it passes, it's like equally weighting the models. And that's a very strong prior, so you use the prior itself for the distribution. And the other ones he's going to show throws that out just to avoid what you're talking about. Does that cover what you meant, Gabe?
Sure, it does.
So how this is done? So this is already something that Norm explained in the morning. I tried to explain it again. So what we're doing is we have
with your either speak loudly or get close.
Okay. We need a. No, it's I try to do that like this. So what we have here is in red are shown again the ellipses that we used to select the models, and the red points correspond to those selected models. And then what we calculated the Voronoi diagram of all those points. So that basically means if I go from this point to that point, this line is exactly on the middle between those 2 points, and it's orthogonal to the line from here to there. And then the same thing, you do that for all point combinations, and that gives you this set of regions. So we get now a region for each of the models.
Nico, what are those black dots? Red dots, I know.
Okay, so basically, so if I do that, then theoretically, the outermost point, so this point, would have infinite area, because then because this would go out to infinity, and this line would go out to infinity. And to constrain that, we just added a fourth ellipse, and then just went out in the same angles as these outer points, just to constrain the outer to constrain the region of the outer models.
All right.
Those are the outer points. And then the other black points are just on the intersection of all those differences. And so each of those regions for each of those models describes some sort of area of influence of the model. So if the area is larger, it means this particular model covers a larger space in ground motion space. So it doesn't really cover it, but it represents a larger range in ground motion space. So therefore, if we want to be uninformative over ground motions, we should just, because this covers a larger range than this, for example, we should give this one a larger range because it has a larger area. But on the other hand, it has, the prior is probably lower because there's less density of points in there. It has a different, it has a relatively high residual, lower likelihood, so therefore we should downweight this. And that's then how the weights are created. So the weights are created based on the area and based on the likelihood and the mean residual inside the area. Did I make myself clear? Okay. All right. So, okay, I think I should have, I had something written there, but, okay, so basically what we're doing is we're calculating some mean statistic inside each area. So basically, what's been done is we're taking this area, we're taking all of the models inside that area, so all of the models that fall inside that area, then calculate the mean of 1 over the residual inside that area, multiply that by the area, or I should say inside that region, and then multiply that by the area of that region, and then we do that for all of those 27 regions, and then we normalize it to 1.
Nico, NGA, it means NGA data.
Yes, that means the NGA, well, it actually
selected.
means the selected subset of the subset underlying the ASK14
You could
model.
do the same thing with simulated data.
And we've actually done the same thing with simulated. And you're getting ahead. Right. So the selected statistics are 1 over the mean residual over each area. So that basically corresponds to 1 over the mean bias. So that means models that have a low mean bias get a high weight. It's actually, so that's the absolute mean bias so that we don't get negative weights. And we calculate that for the NGA data set, so for the real data, and for the simulations. So from that one, we get two sets of weights, based on the NGA data, based on the simulations. We do the same thing for the likelihood. So we calculate the mean likelihood inside each region, multiply that by the area of each region, and then do that for all regions, normalized to 1. That gives us, the likelihood is also a measure of the variability of how the model captures the variability of the data. We do that only for the NGA data set because the variability of the simulations is not calibrated, so we would make some error there. And then we also do this, and this is what Gabe wanted to see, is we do that for something like the prior, which is the value of the PDF, of the density function of our GMPE distribution. So we calculate the mean prior inside each region, multiply that by the area, and then again normalize that to 1. So that is some sort of uninformativeness. If we want to be uninformative, we say all the GMPEs are good, so we're just sampling from that and then just use that as our sampling distribution. All right. And then the subjective part is now we have 4 sets of weights, and those need to be combined into one set. And this is where these numbers here come from. So these weights are then again weighted. So we have a weighted set of weights, which gives us the total weight. And the total weight is based on 0.6 times the weights based on the NGA data set, 0.2 times the weights based on the simulations, and 0.2 based on the prior. And then inside the NGA data set, it's 60% residuals, 40% likelihood.
So let's stop here for a second. And yeah, this looks strange, but it actually makes a lot of sense. Okay, what we're trying to do is separate the subjective judgment from the statistical part. So what Nico talked about on the first 3 up there, once you tell it a statistic there on what you're going to compute, that just gives you weights and they just pop out, and there's nothing that you can argue, oh, that should be a different weight. That metric gives you a set of weights for each of those regions, for each GMPE that is representing the region. So the nice thing about this is it's now allowing you to say, if I want to be seeing how well am I capturing the mean of the NGA data, there's a suite of models that you can use that capture those weights. We could do it, we said, let's do the problem several different times with different weighting schemes. That's fine, but in the end, since it's the same underlying GMPEs, we can just combine the weights at once into a single value. So our subjective evaluation is how much do I want to put on weighting them by the mean bias, or weighting them by the likelihood, or weighting them by the simulated data, or weighting them by a prior saying they all pass, they should all be equally good. So those numbers here, the 0.6s and the 0.4s and the 0.2s, that's all the subjective stuff. Right? And that's really where the judgment and the evaluation is, and that's where you have to justify why you're doing it this way, why not give higher weight to the prior, and so forth. So for these particular cases, we have data in California, so we're saying let's put more emphasis on the data than on the prior. The prior would have been pass-fail. Okay, so we're overwriting. When we do that, we overwrite somewhat the judgments that the developers did themselves. We're going to say, yeah, your model is here, but it's off a bit compared to the data that we think is most relevant, therefore it's downweighted. We want to bring the simulations in, yet we still are having a preference for the empirical data because it's still quite a bit in California for the cases that we're after. And while the simulations are in much better shape now. That's still sort of an evolving part of it. So we would have here a lower weight on those. And that's really kind of where we are on all of this piece. In the East, that would be probably completely different, right? We're going to have almost no data where we really need what's going on other than the distance scaling or the things we talked about yesterday. So it will be more on the different simulation approaches and so forth. But the structure really makes it easier for us to deal with evaluating the models. I don't have to say, I like, ASKA is twice as good as the Bohr model, right? And so I give it twice the weight. All that stuff pops out automatically. That's now an objective calculation once I've decided my evaluation metric, which is really a step forward. I think once we set this up, I was really happy in that I thought we could now sit down and argue what are really the subjective evaluations in a way that you can. So somebody could say, you should have, half a weight on the prior. In fact, Brian said the prior should be everything, right? If you say what the modelers gave is right, then the prior is everything. That's the case, Gabe, where if you have two models identical, then they get more weight. In this case, two identical models get no additional weight for the upper cases because they're all saying they're the same thing. So is that making sense what the difference is? I think this is really a nice framework for separating judgment and subjective parts from things that we can attach statistical weights to.
John.
Nico, one question. This may be better for the discussion, but let me put it up front. Can you talk a little bit about the first two terms, the first two statistical terms? Because it seems to me that the 1 over mu is, well, the likelihood one, because you use a normal tail, kind of tends to give a lot of the weight to a few models.
Yes.
While the other one is very broad, and if you think of it as a distribution shape, it's almost like a 1 over x density, which gives some weight to all of them. Is that desirable?
I think the answer is it's desirable, and that if we put all the weight on the likelihood approach, it collapses it much too strongly to the data, and you'll see that we will be essentially eliminating some of the models so that the range would not capture the GMPEs that went in discarded.
Okay, good.
Because that's like saying re-regress on the data, right? And that's really not what we're trying to do. But if you just do the mean residuals, it's going out forever on the ends, right? It can't tell. So bringing some of the likelihood in starts to chop off the high and low Y values there, because those contours are somewhat parallel, right, going on up.
Yeah, they are.
So the check of it, are you going to get to the CDFs, Nico?
Yeah. So basically,
let him move on, and then I think it'll make more sense.
John had a quick, just one quick thing. So basically, if you weight on the residuals alone, all of these models get the same weight because they all have more or less the mean residual of 0. On the other hand, the likelihood is a bit more like gives very high weight to the models in the center, which really just capture the center and the variability. And but it gives very low weight to the models on the outside. So basically, with the likelihood, you basically have like 2-3 models which get high weight, and everything else is just almost 0. So in this case, you're counteracting the effect of this. All of those models get the same weight, and this model gets a really high weight.
Okay. John Stewart. So my question is, can you explain again what is meant by the prior? I think I get the first 3. Is the prior a published GMPE?
No. So the prior, it's not a good term. So if we have the coefficient distribution, and then that's a multivariate normal distribution. We just take the PDF of that, and then for each of the sampled sets of coefficient, we just evaluate the value of the PDF. And we call that the prior. So that would be an uninformative sampling from the GMPE distribution.
If you think of it as the product of the probabilities of each of the 10 coefficients. So if they're all near the zero, they happen to be near the zero, they're going to have a high product of their probabilities because they'll be near. You're taking 10 samples from a normal distribution, okay? And ones that are near the middle are going to have a higher value, and it's just the product of those probabilities. If you're getting one that one of the parameters is on the tail, then it's a low probability. If all of them are on the tail, it's a very low value. So it's just like sampling. Think of it as sampling a 2D distribution and then go to 10, right? 10.
Okay, so the prior is sampling the
coefficient
that you've developed.
It's
the
likelihood of the coefficient.
So those will tend to be clustered near the middle of each coefficient. The middle of the range for each coefficient.
But yes. Well, yeah.
Yeah. Correct. Each coefficient prefers its center value.
Yeah.
This map, the middle of that map is near the middle of all of them, right?
Yeah.
And so that's just sort of effectively the density of points is almost the same thing, right? It's similar to that. But
you have 15,000 models, right?
Go back to the coefficient distribution, though.
Right.
You have one distribution for the coefficient.
Yeah, that's true. From which you generated 15,000.
Right. Correct. Yeah. And so for each one of those, you can compute the likelihood of those 10 coefficients. So just where they're sampling on their normal distribution, you multiply them all together. That's the number, and then you do that for each one of these. So it's if you believe that covariance matrix, and the difficulty with that approach is it will be sensitive to how many repeated models you have. If you took a model and stuck it in there twice and gave it effectively double the weight, that distribution would change. Right? The other metrics are really insensitive to redundant models, which is a nice thing, okay, and a nice feature to have. Is that fair to say?
Did you ever consider having a different sort of prior, and maybe a different term is needed, where you would have a point that's very close to a published GMPE?
The short answer is no.
Because the advantage of that is that you would, if you would then actually use that, you would get smooth spectra, and there would be certain nice features associated with using that.
It won't be near it at all frequencies.
No.
That's the problem.
Again, we would the GMPEs would be weighted differently at different frequencies. Well, if we just
To some degree, you are because
no, actually, no, that's not true. If we're just basing it on the prior, then no, then not.
Right. So you're interpolating between GMPs. So you are creating many GMPs that are near existing GMPs, slightly different, and perturbations of existing GMPs. Aren't you?
But actually, no, it's also, so if we're just basing it on just on the prior, then because each GMPE has the same likelihood over all frequencies, then we would give the same weight for the GMPEs over all frequencies. If we just base it on the value of the prior. But if we just base it on residuals and everything, then we would get different weights because some GMPEs fit the data well at one particular frequency, but not so well at another.
Really, what we have to do is run hazard with the original DMPEs as well, so that you can see what's happening and what are the net effects. But the concept of this doesn't fit well to going back and saying pick a model near a GMPE or try to find one near each of the published models. We're replacing the GMPEs with a broad continuous function. The GMPEs were
actually just samples from that function.
Right. And there weren't enough of them.
Yeah.
So we're replacing that with what is now gives me a continuous distribution that I can downsample from. And if you try to use them as they are published, it just gets awkward.
Yeah, but I think you are achieving what John wants by that sampling of the 1,000.
We can solve the frequency if you want a smooth spectrum, model to come out that works at all periods, so that it is a full GMPE. That can be solved, but that's going to be another year. That's not going to happen in the time frame we're trying to get through. I think there's some ideas on how to move forward on that. I don't think that's our fundamental problem. And since we're running hazard at every separate frequency right now anyway, it's really not a key issue for us in the end. The UHS is going to come out very smooth. It's not going to have bumps and things like that in it. That's why I think it's useful to show the mean model, and it will probably be a very smooth-looking spectrum. Let's push on.
Okay, so these are the resulting sets of weights. Well, I don't know if you can see that, but so in red, the thick red points are the total weights, and the other colors are then the other sets of weights based on the different statistics. And white, okay, and just forget about the black points. There should be no black points. So what we can see here is, for example, that the likelihood gives high weight to just a few models and gives very, very low weight, almost zero, to most of the other ones. So that gives us a pretty narrow distribution. Whereas, so here we have the residuals gives much more weight to all of the models. And then we have here some models popping out. Those are the models that lie on the zero contour. So they should all get similar weights. It also depends, of course, on the area and how many models are in there. But that's basically the thing. And then these thick red points are just the combined.
That high pink one is the middle, right? That's the prior, so that would be the center of the distribution, probably.
No.
No.
I need to check why that gets a high prior, but
the center is Model 1 would have been the center then?
Model 1 would be the center, yeah. And this is now taking the weights and then calculating the cumulative distribution function. So what we're doing is we have 27 models and we have 27 weights. So for one particular scenario, in this case 7.5 magnitude, distance minus 10 kilometers, and style of faulting 1, so for reverse faulting events, we calculate for each of the 27 models, calculate the prediction, and then combined with the weights, we get a probability distribution. So that's a discrete probability distribution over the weights. And this is just plotted as the CDF, so the cumulative distribution function of that probability, of that discrete probability distribution. And this is all for those different sets of weights. You can see here that the likelihood is pretty steep. So that's almost like a step function. And that's because it gives high weight to just a few models, to just some models which are at the center, or at the center of the predictions of all the models. So that's why this is like really steep, whereas the other one are much more smooth. So basically, each step here is from one model to the next, and then corresponds to the weight that that particular model gets. We also have in black, which is almost indistinguishable from blue, but this is the black. This is the CDF of the GMPEs if I weigh them equally. So in this case, the median prediction of a GMPE gets 80%, plus minus uncertainty gets 10% each, and then each of the GMPEs gets a weight of 1/8, which is 0.125, and then I get a distribution of the GMPEs. Just to compare that with the distribution that we get out of the new models and their sets of weights.
Can you point out the black curve near its median value? It's shifted to, so there's a difference. Our weighted model compared to the GMPEs is shifted to the left, right? So we're getting, in this case, say 5% lower ground motion. So we're not centered on the average of the GMPEs because we use this other information, the data and the simulations as well, to pull it in one direction. Where's the simulations? There, the light blue one, right?
Right.
Yeah. So in this case, the simulations are a little bit to the right, so they're a little bit higher, and that's what we saw on that map. Remember, the simulations were dragged to the other side. So we're not, part of this is, does this set of weights center your model appropriately? That's one of the issues. So we have several different, we have the empirical data we're using, we have the simulated data, and we're using equally weighted GMPEs as our three metrics for centering, right? And it's a weighted average as to where it's centered. And are we getting the broad enough distribution? And that's kind of, Dave, when I was saying the ends work, is this working okay? So that all the other assumptions that went into the model, are we getting something reasonable out? He's still getting a broader distribution here than the GMPEs on the low side, and we're similar to their distribution on the high side for this particular one. But the slopes, if anything's a little flatter than the GMPE slope. So we've broadened the range, right, in what's going on there. And the check of all this is to run through.
So Ken knows that. I've made 900 of those plots, I think. And so just for the PPRP, just to go through all the different scenarios, both for Diablo Canyon and Palo Verde.
Nico, do you have a spectrum of these things, similar to?
No. Well, I have something, so like this. So this is just calculating, so basically from this one, calculating the median, so the 0.5 quantile, and the 5% and 95% quantile, both for the resulting distribution, so for the total weight distribution, and the GMPE distribution with GMPEs equal weighted, which I believe is actually, you wouldn't, well, I don't know. You probably wouldn't do that. So I think it's actually over-representing a little bit the uncertainty if you just use the original GMPEs. And
stay close to the mic.
Right? So here,
Nico,
I can't see the screen.
Nico, a couple of questions over the previous slide. First question is this typical? Because I see a relatively small difference. Is this typical of other cases? Okay, because the differences I see here are not huge between the 5 different approaches.
Other than the likelihood.
The likelihood is always pretty different. So the likelihood is always very steep. There are a couple of scenarios where it gets more different, but in general, it's similar to this.
Yeah, the other thought I have is, roughly speaking, you are talking about a 0.2, 0.25 ln space sigma mu, which is about right.
All right, so this is now a plot of the 0.05, 0.5, and 0.95 quantile of that distribution that we had before for the total weight distribution and for the original GMPE distribution. So in black, we have, based on the GMPEs, And in red, we have it based on the 20 cell, or based on the new sets of models with their total weight. And we see that at some cases, the center is different, which is actually, I mean, it's not so bad, because if the center were the same everywhere, we wouldn't need to go through all of that. But so we're actually recentering from the center of the GMP distribution. But we're also close, which is also good, because it would be very surprising if we were like really far, if the GMPEs, or if we were really far off from the GMPEs. And then the other one shows then the range of the new distribution and of the original GMPEs. So this is for against magnitude, against distance, and this is for a spectrum. So the media, or the 0.5 quantile of the resulting total weight GMP new model distribution is fairly smooth, except for those two frequencies there. I need to check what's going on there. And that's it. So that's what was done for SWUS. And now the question is, what can be done for NGA-East, and I think that is open for discussion. Basically, what we have for, or what's supposed to come out of NGA-East is there's a calculation of response spectra based on different models and based on carrying through all the uncertainties. We have based on simulations, based on the empirical Fourier spectrum models. The question is, do they all fall on the, do they capture the same range? So we can just check that, use it by just calculating maps of all the predictions for the PSA. We can use the generated PSA values, try to fit them to a common functional form, and then get to some sort of GMPE distribution. And to be honest, once we have a GMPE distribution, I think it would be much better just to publish mean and covariance instead of breaking it down to a discrete set of models. But well, this is open for discussion. And then we can do the same thing, because everything is based on the Fourier spectrum, and well, not everything, but a lot of it is based on Fourier spectrum and duration. And if we then, I mean, we're probably always going to check against the response spectrum, how's the response spectral fit. But when we generate the new models, we can still compare that to the response spectral data that we have, and against the finite fault simulations once they are there, and treat them exactly the same as in SWUS. Well, that's pretty much all I have.
Says you have 3 more slides.
Yes, and that's thanks to, I forgot to put Gabe on there actually, but also the PPRP played a major role in this. They've seen that a couple of times in all the iterations. And
okay. So let's go. So
Vladimir has a question.
So for simulations, you have also different simulations, right?
Right. Okay. But I mean, we can just treat them. Well, it depends if we have something like a map of the models. We can treat the simulations of that as data, make a contour plot, and try to see what's going on.
Okay, Vladimir Greiser, NRC. I'm trying to come back to a few statements made here. First of all, as far as I understand, you want initially this GMPs to be as much as independent as possible. That was kind of one of the assumptions that we are covering epistemic uncertainty. In the meantime, I also understood from talking to you that so far you can only cover GMPs which have similar or same approximation functions. My question is, if do you have any plans to accommodate something which has different? I'm not talking about what is done for Diablo and Palo Verde. I'm talking about the future. Do you plan to accommodate other functional form if you see that this GMP makes sense from physical point of view?
Yes, because the functional form needs to be adjusted to the application. So there's not one functional form that is best. It needs to be adjusted to the sets of models that are possible and that are and to the application that is used. So it's always a matter of practicality. So the question, and then how reliable can you fit each GMPE to that particular functional form, and how reliable can you estimate the correlations so that in the end you don't sample really unphysical model, which is if you have a very, very flexible functional form, it's easier to sample unphysical models in the end. So if you have a functional form that can accommodate everything, or if you do something non-parametric and then you sample new things, with a non-parametric form you can capture everything, but you can also just sample everything, you know. And so, but this is not a fixed functional form that is the end.
I think we would say a limitation of this approach is conceptually the same as the limitation of a scaled backbone approach, where we're changing it up and down, but we're not getting all of the fine interest, details that could happen. The way to deal with let's say we have one model with a really different functional form developed into, or different approach, and we think it's physically reasonable and we want to get it in there, you can still put that model and project it into the space that we're using in the same way, but without reparametrizing it into this particular form. And that's probably the way to do it, because I think the strength of what they're doing here comes from the common form. That allows you to get the covariance matrix on coefficients, and it can't be overly complicated or there'll be too much slop in there and you'll get the non-physical forms that Nico was talking about. But you can still evaluate things that are really different and say, am I capturing what they look like or their form? And in the end, we'll probably have to run hazard to see, does this actually mimic capture the range of hazard? Because it's really not, well, Nico's right, you could re-optimize this for a different problem. This was optimized for Diablo Canyon and for rock sites and so forth. Trying to make it too general defeats the purpose of what we're trying to do here.
But I think we have one advantage with NGA-East is that we're developing models that are span the range, and we can make sure that we give ourselves the flexibility in our functional form. We're not going to deal with hanging wall effects. This is all gone. We're not dealing with, there's a lot of things that we're not going to deal with in NGA-East 1.
I'm not sure.
Good luck find the record on the hanging wall fault, but it's not.
Doesn't mean it's not there.
Okay.
Lack of data doesn't mean non-existent.
Well, originally we said we were not going to try to model that in NGA-East. Well, we have 3 months. We can do everything.
I think, Christine, we should not force it to think, let's see what...
Okay, let's see where it goes. But I guess what I'm trying to say here is that, for example, we could play with the functional form, and as we develop those models to make it easier to compare, and the magnitude scaling breaking point could, doesn't have to be... Then we can use the existing GMPs and plot them in a map space. We can also use them in different ways to either generate, again, fit them in the new form or just as a check. We have a bit of flexibility, I think, here in the way we're working. The simulations, we can use them to constrain our what we call empirical model, which is actually empirical with seismological constraints. We can develop the model there, but we could also check against residuals with those simulations at the end. Those are different ways that we can play with the same tools and kind of span our data space, and either we brainstorm with Nico for fun sometimes about that. We can use different data sets. So those are the things we're going to look at as part of the evaluation and development as well.
One uniqueness for NGA-East is also the empirical data is good up to a magnitude, and then the rest. So you have the combination of different quality of the data, simulation, one range, empirical.
Right. I mean,
okay, I'll just jump in here. So, just Rob Graves, following on what Vladimir had asked, or maybe expanding on that, does this also provide a path forward for incorporating simulations, in that it's just another model in a sense? The simulation isn't parameterized in the same way as the GMPE, but it gives you ground motion predictions.
Answer to that. There's one way we can use the simulations to constrain the part where we don't have data for what we call the empirical models. We can constrain that. We can also use the simulations ground motion data underlying to compute, the residuals and to span the space, the background maps we have there. So those are things I hope we'll all do, because this helps us to make sure we capture everything that was in the simulations that maybe we parameterize in a way that's, leaving that out. But yes, there's different ways to use the same data, if that makes sense.
This is Linda. I have a question for Nico, being a proponent expert of the approach. What kind of problems do you foresee for NGA-East needing to be applicable on a much broader range with this approach?
Well, the thing is that the data is, because the data is relatively sparse, probably the models will be simpler than in the West. So it's easier to just fit them to a simple functional form, and then we can. Oh, I need to speak. And then we can just do the same approach, just sample from that, and yeah. No.
Okay, actually.
I agree with what Nico's getting at is the models in the East are actually pretty simple. They don't have all of this stuff that we've thrown onto the Western models. So I don't see the fitting is to be the place that falls apart. The issue of how we treat the simulations is an important one. Are they treated as data, which we combine with the empirical smaller magnitudes and create a model? Or are they treated as an underlying data set, or both, and then you're reusing them, and that's a bit circular? You better fit, but at least it gives you a way to check the previous generation of models, or ones that were based on point source models and so forth, against what those are, and so forth.
mean, if you just treat the simulations as data and combine them with the empirical data, you still have the problem of the calibration of the variability. If you just use that as normal data, then you will get the sigma that's coming out of the regression will be wrong. Well,
but we're going to throw that sigma away other than for RVT. So I think we're okay. That we probably would need in the regression two different sigmas for the empirical data and for the simulation, so the likelihoods would be done properly.
Nico, can you go to a slide for NGA-East, the issues? I have a question. Yeah.
I mean, the other thing is you can just use you can just fit thousands of you can just fit different functional forms to the empirical data that extrapolate differently. Then just use from each of them sample from the posterior distribution, put them all on the map, and then compare that with the see where they fall at first of all, and then use the simulations as an underlying data set and compare them the same way we use C, and then say, okay, well, this particular extrapolation works better than that particular extrapolation. And they are overlapping, yes or no. And
so this last bullet was what Norm was talking about. So when you say evaluation of the models with data, what kind of data? Empirical data or combination of empirical and simulation, or separate, basically?
Probably separate. And the other thing is if you want to I mean, what's coming out is is a distribution of models, I believe. Either Bayesian posterior or just sampling from the standard error and covariance of the coefficients. But if you want to downsample that, that would be a viable approach.
Then, Nico, before we started the discussion, you made a point that I missed. What did you say that you go to Fourier spectra? What you had a suggestion before we started discussion.
No, well, basically, I mean, the other thing is there will be a model for the Fourier spectrum, and then there will be a duration model, and then. Well, if we do everything correctly, that should be calibrated to the response spectral data, but it's not a must. So it doesn't necessarily give you a calibration to the response spectrum. But then we could just simulate a bunch of different models or a bunch of different response spectral data based on Fourier spectrum, based on duration, and then plot them all on the map and compare that to the response spectral data.
Okay, Gabe, you had a question. Yeah, I had a question, more of a comment in terms of and actually relates to Linda's question of what will be different in NGA-East. And one thing that comes to mind is that the data are going to be much more limited, and they're going to be, I wanted to say that the wrong magnitudes and distances. And one way we dealt with in the 2013 work was giving weights to those magnitude and distance ranges. That's something that should be kept in mind as an option. The other thing is there are also a lot of those sites where the characterization of the site is a little bit questionable. That also needs to be taken into account. Anytime you develop weights based on the data, you have to keep those two issues in the back of your mind and handle them somehow.
Yes, I think we have a path forward for those issues. The weights for the magnitude and distance is something we need to think about a little bit more. So, yes.
I wouldn't say weights. I would say we would choose different subsets of data and see and look what happens. The site conditions is an issue. We're planning to be taking try to take this site out through the site terms, but still it has to be relative to something. And there may be subsets of the data, again, of a more reliable data and a less reliable one that you could see what the maps are looking like. The range is going to be bigger than what you've been looking at here. I think we could conclude that Anything?
No, John had a question.
Well, I have a question on a different point, so if you want to follow up on that line of discussion. Okay. So, John Stewart. And so I just want to maybe ask almost a philosophical question related to this. One of the approaches, one of the assumptions in the approach is common functional form. And whether we're talking east or west, I mean, I think a legitimate source of epistemic uncertainty is people might want to capture physics in different ways, or, you know, we're talking about, just to give an example, we're talking mostly about rock GMPEs, but if you go to soil, one model might have a basin effect, another one might not. One model might have no nonlinear site term, another one might have a nonlinear site term. Different ways of representing the physics that could represent a reasonable range of alternate interpretations. And so just when you go to an approach that forces a particular functional form, you lose the ability to capture that, which is part of the epistemic uncertainty. Now, it may all come out in the wash, and Norm's basically saying as long as you end up with something that has a wide enough range, it's okay. But it just seems limiting. Now, I understand that in the case of hanging wall, you deal with that on a site-specific basis for that site based on a different set of branches in the logic tree. And maybe that's generally how you have to do it. For every site, what's important, extend what you've done to bring those things in. But is that a safe summary of the method, that you're capturing a certain core set of variability, and if there's other physical issues that may be going on, whether it's hanging wall or basins or whatever, you have to bring that in through separate branches?
But, so that's just the way it was done here, but that theoretically we could use, makes it a bit more difficult, but we could use different functional forms, and then put weight that would give us different distributions for those coefficients, for the coefficients of the different functional forms, and then give weights on those different distributions. And we have, basically put a logic tree on those two different distributions, which is actually the same thing, which actually is done for Palo Verde, where the it's the same functional form, but it's two different parameterizations using RGB and RUP. But you can also, you could include 10 different functional forms and then put a multinomial distribution over that and say, okay, this functional form is 0.1, this has 0.2 weight, and then sample from that, and then base your evaluation on that one. And since we're at least as far as I understand it, but
I think, John, your fundamental assumption is not quite the way I would put it. It's not that we say everything has a functional form and we can capture the variability. The fundamental assumption here is that the space of ground motion models is continuous. Okay? As soon as you go to that, and let's say you have two different physical models and they're separated, we would say in between there is also a range of models. Now, if you say, no, it's either this or that and there's no in between, that doesn't work in this framework. This framework fundamentally says it's a continuous distribution that we want to now sample. And how do you get to filling in that continuous distribution? I think that's the concept that you ought to have in the back of your mind. And did our distribution bring, get all the way out to all of those different approaches?
Okay, I'm going to try and formulate. I'm still not sure I can formulate my question coherently, but I'm going to try. So, to me, it seems like the problem is defining that continuous distribution. And I see that this framework works very well for the example of the SWUS project, where you already have these nice GMPEs that are already defined, and I can see how you can fill out the continuous distribution nicely in that application. What I'm struggling with is whether this is really going to be an effective tool for the East, given the sort of lack of clarity in how to define that continuous distribution space.
Do you consider that the space in the East of ground motion models should be continuous? So that's the question, right? And so if not, this method doesn't work for you. But that's fundamentally what we're getting. That's what I was trying to start out this morning, saying we were before just doing continuous distribution on a parameter. Now we're extending that concept to continuous distribution on the GMPEs. And if you accept that's what we're trying to get at the East, it'll be more uncertain. There'll be a broader range, but there shouldn't be a suite of models and then a gap and then another suite of models. Everything should be filled in. That's what we're trying to accomplish with this method.
Yeah. Following up on Gail's
And
question, go ahead.
just to finish, I guess I agree that it should be a continuous distribution. What I'm not confident of is how well we can define a continuous distribution, and I'm not sure of how that inability will interact with this framework and whether we're going to get something useful out of it, given that.
Can I think my comments are related to that one. For example, two issues that come to mind along the lines of what Gail said is you may not, you're going to have very few GMPs. So it may be that, I guess, with the exception.
No, all right. But
you may run into a situation along the lines of what Gail is saying, that, for example, you may not get much magnitude scaling from existing GMPs, so you may have to artificially reduce the correlation, reduce the covariance, for example, on the covariant matrix, because that covariant matrix may be based on very few models. The other issue is one piece of data you used in NGA West, if I understand what you did, was the Alatik-Young's epistemic uncertainty. I guess with the exception of the 2013 work, you may not have an equivalent piece to use here.
So that sets a minimum. But yes, so we have to wrap this up so we can move on to other things. We'll talk more about this in October, but everybody will have had time to digest and then how you all understand it. So when we go in October, it's going to make sense. But again, the idea of the peer NGA-East GMPs, that is our idea to span a wide range with those and make sure that we capture some of the epistemic in there and different scaling and based also on empirical past studies and all that, and capture that with the suite of GMPs that will then, what I envision, is combined with existing GMPs into a functional form that to create this continuous distribution to span the space. That's kind of in a nutshell, and what a beautiful conclusion.
Yeah.
And thank you, Nico. And if you have other questions, he's around for quite a while more, and I guess it's my turn to talk.
Yeah. I want to make just one comment. This is made as PPRP, as a PPRP member at least. That by October we should see preliminary results.
Yes, yes, absolutely. But this is really coming together. It's very nice, and that's where we see here the creative working together with SWUS and other people, and as well as the topic I'll bring on now, that we pool resources to solve those issues. We had planned early on to use a methodology similar to, Salmon's maps in NGA-East. We didn't have the funding to go and do it. So most of the development was now completed. We've seen it applied in concrete ways, and now these distances in Salmon's map make sense, which before to me didn't make sense. What's a one? What's a, you know? So we're going to be able to apply that. So I'm going to try to go faster on my own talk. So this is, again, a very large collaboration, a lot of people involved in this, and a working group that's been working for 2 years on that, mostly from funding from SWUS in collaboration with SCHAC, the Southern California Earthquake Center. Lots of people involved, not just the modelers, but also software developers, and we developed tools to make this work. And I was part of the process from very early on to make sure that the way the validations were done would work for NGA-East. So it also worked for SWUS, of course, and we all had common goals. So a lot of you in this room have seen this talk in various forms and lengths, and I'm sorry for the repetition for most people, but this is the opportunity for the PPRP to have a formal description of the validation process. So that's why I'm going to bore you to death again with that. But it's okay. So I sound negative. This is a very exciting project, and everybody worked really hard. And we now have submitted collectively a set of 8 papers to SRL that summarize everything that I'm going to talk about today and more. So I'm going to talk about the validation framework and some of the tools we use to evaluate the different simulation methods. And then after lunch, Dr. Drager is going to go over the differences in the description of the methods themselves. And after that, we'll talk about how we're going to parameterize the forward simulation. So how we're going to generate ground motions for magnitude distance ranges where we don't have data. So that's how this the rest of the day is going to go. Okay, so introduction was done. We're going to talk about the validation framework was done in 2 parts. What we call part A is validation against recorded ground motions for different events. So I'll talk about the event and record selection for that and how we corrected the records for site conditions. Part B is a validation against GMPs. So that's to check the centering of the models. Are we about right? Are we where we have data? We should match the empirical models, okay, that are also based on data. And now I'll talk about the evaluation a little bit, and that's it. So again, this is a very large collaborative project. It was driven by the needs of SWUS, NGA-East, and the NGA West project, who also plan to make more extensive use of simulations. The Southern California Earthquake Center, SCHAC, they have developed a broadband platform, so that's a software package or set of packages to compute ground motion simulations. And now we've worked really closely with them to include more post-processing and computation so that we have products to evaluate those methods. So their collaboration was amazing. So this is critical to the success of this, 2 centers and SWUS collaboration. So past validations, and I'll always wink at Rob, they were done this way wiggle to wiggle comparison. We should keep on doing that in the future to understand what's going on in terms of seismology, but that's not what we're after. We have immediate needs for PSA validation, so this whole validation exercise was designed to become provide a quantitative validation with the mindset that we're going to use that in forward simulation, so for engineering problems. So when I talk about forward simulations, again, generating ground motion data where we don't have it. So the objective relevant to NGA-East is that quantitative validation to supplement the recorded data set for development of GMPs and hazard analysis. Okay, so that big gap we had in the magnitude distance range in the East, that's where we're going to use simulations for. So again, we're after PSA here from 0.1 to 100 hertz. And the validation here is, again, all for mean ground motions only. We're not looking at standard deviations at all of the simulations. Okay? We're only trying to get mean ground motions from the simulations. Key lessons learned from past validations over the last 30 years or so. in which a lot of people were involved, including Norm and Walt Silva and various other people, and what we learned from that. We need more transparency with the process. We cannot have the modelers themselves validate their code and not know what's been used as input. We need to validate against many events. One model may work really well for one event, Loma Prieta, and then doesn't extrapolate or work for anything else. So we allow them to have trade-offs that each event doesn't match as well, maybe, as you could tweak all the parameters and turn all the knobs to make it work. But in average, you want to make sure the models can capture the events, and with some misfits. We need a clear documentation of what are fixed and optimized parameters from the modelers for each region. So what magnitude area scaling you use, what kind of stress parameter if you use a stochastic approach. These are to be regional quantities, but then for an event, maybe you tweak, the something in it, but you need to tell us if it's for Western U.S., then you need to make sure my model requires that you have 0.2 magnitude plus or something like that. Whatever rules, we need to know what is fixed and what are rule-based and what are region-specific. We need a source description that is consistent between methods. So those of you that were at our SHAC Workshop 1B saw what I would call a very interesting experience of diversity of the results. We tried to do this. We learned a lot from it. Everybody used an inverted source model that was different. Everybody plotted on different scales. We didn't have things that we could compare. So now with this working group, we have all the modelers interacting, and we make a collective decision as a group of what are the rules to be used to model Loma Prieta. We shied away from going into an inverted model. We use rules that the same way we would model a future event, we don't know exactly how it's going to be. It has a certain magnitude, okay? So then everybody used the same geometry. So that's what we mean by source here, the same source description. Geometry, the depth, the dip, so the area and all those things. So it's consistent, okay? We use a unique crustal structure for all the models, and right now it's all limited to 1D velocity structures. That is given different models, as you will see this afternoon, use different ways of modeling that 1D velocity structures. For XM, it's just M factors, while for methods that use green functions, they actually propagate the waves through that structure, so it changes, but it has to be at least consistent. We consider multiple source realization, so most of these models have some kind of randomization or a way to their source generator. So once we have set the geometry of the source, they can have different slip distributions using their own internal rules and all that. That's part of their epistemic differences in there. So that's it. We have 50 realizations of each event, okay? We run the simulation, so that means we don't use an inverted source. If we use an inverted slip distribution, we would get a better fit, but we wouldn't know what to do in the future because we don't know what that source is going to look like. So that's the idea here. And also, we don't want a circular reference. So I do an inversion, which is, the inverse of a simulation. I get this beautiful, source. I put it back. Of course, my results are going to look good. So we wanted to shy away from that. So a lot of those decisions were made to make sure that when we go in the forward sense, we know what we're missing or capturing in terms of uncertainty or things unknown, okay? We run the simulations for reference site conditions, and we correct the data with empirical site factors. So we compute PSA from the recorded data, and then we take empirical site factors to take that out to a reference condition. The reason for that is that side effects, linear and nonlinear, right now are not correctly implemented on our broadband platform. They were in a crude way, but some methods couldn't use them, and then it becomes like, what are you comparing with, right? So it says, okay, everybody, we fixed the velocity structure, whatever it is for a region, that's your reference. We're going to correct the data with empirical side factors that we believe are more well constrained, and we better understand how it works, and we don't want to put the burden of site response on the seismologist, okay? So that's a choice we've made up front. The disadvantage to that is where we correct PSA. Therefore, the waveforms cannot really be compared because the recording could have been on, 500 meters per second, but our simulations are 4,000. We cannot fully compare the waveforms. That's the disadvantage. Okay, then we also make all the validation metrics, computations, and plots and everything in uniform units and scales. It seems silly, but even if you tell people to do so, it doesn't come out right. So now it's all done on the platform, and it's done uniformly. Okay, and then we need to tie into specific broadband platform version. We know which code. The codes are in constant evolution, and through this exercise, we allow people to modify their model to get a better fit, and that's kind of a feedback loop, and we go back and play with that. So SWUS used version 13.6 of the broadband platform validation, and NGA-East we use version 14.3. So for example, when SWUS did their simulations, there was one method that didn't pass. They worked on it, they changed things, and in 14.3 we have the opportunity to be able to use it. So again, two validation schemes, one based on comparison with recorded ground motions and the other one with GMPs. So let's look at that. I'm going to skip this. I already explained that. PPRP will have that figure. They can look at it if they want tonight, if they're bored. Okay, the simulation methods are evaluated that Doug will go over. There's two that are broadband deterministic methods. So CSM, which actually was not ready for evaluation at this point, UCSB, led by Ralph Archuleta, XSIM, which is a stochastic finite fault. We're all talking about finite fault here, by Caron, Asaturians, and Gale. Graves and Pitarka by Graves and Pitarka. Those are hybrid methods, and then the SDSU toolbox, also a hybrid method by Kim Olson. So we have 4 methods that were tested. We also checked for other methods, point source and finite fault outside of the platform, including SMSIM and Silva stochastic models that include a finite fault. We compare with GMPs. We've done that with only the west ones. We just coded up the eastern GMPs just to check the attenuation, just as a reality check, but these plots are not ready yet. Okay, then big scheme, big picture. We want to have a lot of events, as I mentioned, so there's now 25 events that have been selected, and 13 of which that are shown here for which we have completed the validation. We try to span a different tectonic regime environments, span a wide range of magnitude from 4.4 to 7.62, different mechanisms, and we wanted to have well-recorded earthquakes. So we have 17 earthquakes with more than 40 records. We select a subset of stations that we wanted to limit to 40. 40 is a good number. It's large enough that we can compute, averages and statistics on it, but it's also manageable. And so the key for the station selection, I'm not going to go over much, but if you take the whole data set, I have a picture to show you the idea here. If we take the whole data set using the Northwood example, using PSA, say, or PGA here, we have a cloud of points that consists of those red points and the gray points together, okay? We run a simple model, the magnitude distance regression. That's the black line. The black line is for the statistics. It's really the median model for all the data points. Then we randomly select a subset of 40, and we generate like 10,000 sets, as much as we can, given the probabilities there. And then we find the one that has the median prediction in red, that is the closest to the median prediction of the full set. So that makes sure we don't just pick sites that are weird or high or low. We just make sure that the subset is representative of the larger set. Whenever we had the flexibility, we made sure to capture, in some cases, more of the close-in stations if we had a lot. But these basically were separated in distance bins where we made sure to sample from the different distance bins, okay? And we do that for all 3 periods. We also check that the standard deviation of the full set and the selected set are very close. The idea, pick a subset that's representative of the whole set, okay? We correct the reference rock condition that we use. I'm going to focus on CINA here and will not go much into details. But we selected, for the validation, reference rock of 1,000. When we first did this, and we had a workshop 2 years ago, or last year, December, was that last year? 2012, December. On the simulations, we had originally tried that with a velocity structure that went to 3,000 meters per second. But we felt that the site corrections and the uncertainty in there was so, we were asking so much of the site corrections that we were probably having issues with that. So we did it for 1,000, where all the sites are closer, and maybe if there are potential issues with the site corrections, it's fairly small. And even if we have differences of 30%, you'll see that if it was, and it's not, it's less than that, it's really not important for the fit. You'll see how far or how close we are, but it's in the noise. Okay, so we used the empirical amplification recommendations from the Geotech Working Group memo. Basically, it's a two-step approach. We have a linear scaling from whatever is the recorded VS30 to 760. And then it follows the linear scaling using a modified Atkinson and Bohr 06 amplification function to go from 760 to our reference, okay? And that would allow us to go to 2,000 or very hard rock that we'll use as well in the future. And then we combine those two together to correct the recorded site, the recorded ground motion. Okay. Nomenclature. For each scenario, we have we specify the source, so that's the same input for everybody. The magnitude, it's not MW, it's bold M. Geometry, location, hypocenter, all that is fixed for everybody. The path, we again use a consistent 1D velocity. The site, as you know, we've corrected that. For Western events, we use the BSSA site models. Didn't go over that, and for the East, you now know what we've used. For each scenario, then, each of the 13 events we modeled, there are seismograms generated for 50 source realizations, okay, at about 40 stations whenever possible, and 2 horizontal components. So we have 4,000 time series per method per scenario. It's a lot of data. We compute PSA after that and compare. Ground motion products, we do a qualitative evaluation of velocity time series and USET plots as shown here, just to make sure that the ground motions, they look like ground motions and not spikograms. We cannot compare directly because they have different VS30s, but this is a check, a reality check, intermediate process, product. Here we plot a PSA with period. Again, this was done in period space. But here you see the Northridge recorded ground motion in blue, and the green is one of the realizations from a given simulation method. I plot here the dashed line. Red shows the high pass filter, where basically we start to lose stations. And you will see when we look at our statistics that we as the period increases, we start to lose data because of quality, and so we put that in our plots so that your eye can be guided and not put too much weight on those results. So here are the what we call goodness of fit measures for PSA. So here we have the period, and here we plot residuals. It's again data minus model. So if that's 0, it means that the simulations are right on the data. If it's less, it means they overpredict. So negative values is overprediction, and positive value is underprediction. This is an example here of one realization of the source where we have done that residuals computation. The red line is the mean. The yellow band is the 95% confidence interval of the mean, and the cyan band is the standard deviation. And that's what I meant here for Northridge. Loma Prieta here, we're starting to lose data, so the yellow band becomes wider. Okay? That means that this comparison here is less reliable. We don't have all 40 stations, all 40 recordings. That's done at all the periods, okay? Then our plot that we actually use to do the evaluation, that's a different scenario, but same concept. We just have a different color scheme that's a bit more girly because I was involved in selecting the colors. No, it's just that it's clear that you're looking at 1 realization and 50 realizations. So this one here is the same plot as on the left, except the 50 realizations are factored in here, okay? So, and again, the mean, the confidence interval, and the standard deviation of the results, okay? So that's the key that we'll talk about now, where I don't have much time. Oh, I have time, okay. So other ground motions products. We plot also the average goodness of fit with distance of all the realizations. So what you cannot see the scales here, I know. On the y-axis is the same residuals, data minus model in log space. And now on the x-axis is distance, okay? Each line, each point with its error bar that you might not be able to see is a station. And we basically have the misfit at that station from all the realizations. So the mean is the circle, and the error bars are the min and the max. The use of this, it's useful because it allows us to see if there's a systematic trend with distance. For example, as we see here, maybe we have an issue with Q in this case. As you get to larger distances or geometrical spreading, you can see if you have regional bias with distance. So that tells us more than just looking at the period where everything is mushed together, okay? We have the same, another plot. Again, this was for a subset of 8 periods that we picked. We have also to try to understand maybe directional differences or directivity and things like that. We plot the residuals in this color code here on different maps, on maps for these different periods. The event is hard to see, but there's a yellow star here with the trace of the fault. That was Saguenay, so that's why it's so small. And then you see the different residuals, and we can see whether it's balanced or there's, I say, overprediction in the direction of the fault or something like that. Okay, so that's all things that we look at to make sure the results make sense internally. The goodness of fit plots are also generated for GMPs. And so far, we've only done that for the West 1 models, but that allows us to see trends such as event terms, for example. And when we see that the empirical models and the simulations follow the same trend, at least it tells us, oh, maybe that's an event term we see in there. It allows us to kind of take that away as, oh, your models are over-predicting at 1 second. Yes, but the data is low, so relative to the pool, the larger pool of data used for the GMPs. So we use those as a check as well. Okay, that was part A. Part B, we have basically selected a subset of scenarios where the NGA West 1 and 2 were well constrained by data at 20 or 50 kilometers. And we came up with these 4 different scenarios, 2 strike slip and 2 reverse. And for these, what we do is we run 50 realizations of the source again at a bunch of stations at 20 and 50 kilometers. But then we randomize the whole hypocenter location. So when we did the scenarios that were based on recorded events, the only thing we really took from that event is the hypocenter, because that's something we knew, okay, so to check the match. When we do the test with the GMPs, because GMPs are developed with a broader set of data to be a bit more on a level footing, we made sure that the hypocenter is randomized as well inside the randomized source. So we make sure we capture that. Simulations were done for 2 velocity models, Northern California and Southern California. Again, calibration here is done where we have data, where we understand the models, so for ATRs, active tectonic regions. So summary of the simulated events that we have done and evaluated. In blue are all the Western U.S. events, for which, and the magnitude on the Y, and the distance on the x-axis. And then we have 2 Japanese events in red, and our 3 eastern events, Rivière du Loup, Mineral, and Saguenay, are here and in green. So that spans our space of evaluation of the methods, okay? Evaluation was done by a SCHEC-led review panel, which a few people here were a part of: Doug Drager, Greg Baroza, Stephen Day, myself, Tom Jordan, Paul Spudich, and John Stewart were part of that. And what they had to do to review is the modeler's documentation, that Doug will go over a summary of that, and their self-assessment based on the results they've seen. My method should work. I see no objection for it to work to a 9.2 or I wanted to get Rob's attention, but yes. And then all the broadband platform results for Part A and Part B were used for this assessment. Then they came up with rules to define, okay, this is a passing method, this is a failing method, and that's what I'll go over. So of course we have these plots, and they're nice and informative, but we want to aggregate all this in a metric that we can look at. So we compute two things from these plots. We compute the mean bias. So imagine right now that I have a line that I underpredict at low frequencies and overpredict at, low period and overpredict at a longer period. If I take the mean bias, I might have 0. It might tell me the method works great, but no, there's a bias all around, okay? So we also look then at the mean absolute bias. So we take the absolute of the bias, take the mean of that. This, we could also have a case where it's fairly low, but systematically always low or high. So by looking at both, it gives us a way to kind of weigh these things and those trade-offs that there is in those two things. We define the failure threshold of a factor of 2 in log units, so that's 0.7 or so. And then we define thresholds, and there's a lot of judgment involved in that. We've defined that it's probably okay if you're between the 0.5 and 0.7 and above 0.35. So I'm going to show you figures and tables you won't be able to read. That's okay. Here's the only one you'll be able to read. It's to explain the concept of the table. So we set our failure threshold here, and the unacceptable threshold, like beyond that point the method we think is failing. Okay, what we have is we have here a single period range, 0.01 to 1 second, and a distance range of 0 to 5. A lot of this is gray because we don't have data. What you have here is listed the events from active tectonic regions in increasing magnitude, and then our 3 eastern events, okay? And each of these cells, we have a method, so here UCSB, and the first one is the mean bias, which can be positive or negative, and then the second column is the mean absolute bias, okay? So we can look at those, and we do, and we see things, okay? Okay, so this is what we're looking at. Now we reproduce that for different period bands and distant bands as well. So I'm going to show you this table that you won't be able to read that aggregates all this. So UCSB, XM, Graves and Pitarca, SDSU, and then the GMPs. Different period bands here, different distance bands here. If you just focus on the colors, because that's the only thing you see that at fairly short period in a certain distance range, it looks pretty good for the simulations. It's all green according to our criterion, so it means that it's good. As we get to longer periods, sometimes it's on and off depending on the method. But that's basically what we use to evaluate this, part of the process. Okay. Then we use a combined metric, okay, that combines those two things we talked about, the mean bias and the mean absolute bias. The way we do that is we call that the CGOF, combined goodness of fit. We take half of the mean absolute bias and half of the absolute of the mean bias. I'll let that process, okay? And so we're just weighting those two things equally and coming up with an absolute number, positive number. One is the average of the absolute, the other one is the absolute of the average, okay? And we take half of each. So that's our combined metric, Okay, I'm going to show you our magic table here. And again, we set a failure threshold and passing threshold, but we found that this was not very informative. So let's go to the next step. We can normalize it then. So if we take the combined goodness of fit from the simulation method relative to the GMPs, what we can tell now is whether the simulations perform better than the GMPs or worse than the GMPs. That's the table I want you guys to focus on. Again, short period range, so 0.01 to 0.1, 0.1 to 1, 1 to 3, and larger than 3 seconds. And then those distance bins. So the yellow is the GMP's combined goodness of fit. Whenever it's green, it means that the simulations predict the data better than the GMPs we've used. If it's red, it's worse. The threshold is very small, though. It's just better or worse, okay? And we see that in general, those methods work really well. What is kind of funny, though, well, ironic, is that at longer periods, say larger than 3 seconds or larger than 1 second in some cases, depending on the distance bins, the simulations don't do as good as a job, and most of them, what's happening is they're over-predicting ground motions at long periods. So that's kind of the general conclusion we have from this validation here. Okay, then there's one more thing we look at. We talked about this attenuation bias, and then John Stewart came up with this idea of looking at this in this clever way, again, to aggregate all the data. So here we bin the goodness of fit. This is, again, you don't need to worry about the details. This is our residuals, right? Again, data minus model log space. And then we have the log of the distance in here, and we bin all our goodness, our residuals per distance for a given method, and we plot them out here, and we do a regression of the results, okay? And then what we're trying to do here is, like, for example, here there's a systematic trend that we start to under-predict at larger distances. And so what the test to check whether a method is passing or not is that if you can fit the zero line within that 95% confidence interval shown by the red lines here, if you can fit a slope, a line of zero slope, the method passes. If you can't, it fails. So in that case here, I can't put a line, a flat line in this interval. But here I can easily fit it through here. So this bin passes, this bin fails. Okay? So in a nutshell, if we summarize everything we've seen from these plots with the distance bias, all these methods have their the zero line that goes through the zero slope, through the 95% confidence interval. The only one that's not fully passing is UCSB at long periods when we consider all the scenarios together. If I take out a few scenarios, suddenly it passes, and then other red pops up, but it's marginal. The methods are working well. Part B was much simpler. I'm almost done. Part B was simpler. We just plot the average of the NGA West 1 scenarios in this black line. That's a response spectral shape space. You're used to that. And then we define an acceptance criteria that's based on the range of models in the West up and down. And we check whether the mean of the simulations, which are represented by those box plots and the red lines, the red dots, are fitting with within those criteria. Okay, those bands. Those bands span a factor of more than 3. That's a pretty generous range, but it's just to make sure that we have about the general spectral shape correct, and that there's no sudden changes with periods, and also that we're about mean-centered. So any method that didn't exceed the dashed lines was passing, and they all did. So I'm taking the review panel findings from last year when we did version 13.6 as an official review panel, and then we've reassessed that recently with the 14.3 and we have a lot of detail in the methodologies, the full validation scheme, and the evaluation, and a set of 8 papers coming up in the SRL focus issue soon. It's under review. So the broadband platform objective of a version-controlled numerical testbed with common post-processing tools was successful at producing results that we can evaluate. All the currently methods should continue to improve, and they are. There's a lot of changes happening all the time with tweaks here and there and adjusting the models. 4 methods based on 14.3 are now passing based on the Western U.S. criteria and marginally passing on the Eastern. You'll see what issues we have, but I think it's not just the method, it's the data we have in the East. So right now we have 4 methods that are expected to provide reliable results from 0.01 to 3 seconds. And from the magnitude range, I could extend here for about 5.5 to 7.2. So the methods are also deemed suitable for extrapolation to larger magnitudes, such as 8, but for the purpose of assessing relative trends or effects. Okay. If we need to have absolute amplitudes, we need to be careful in the way we use them. So we all need to be careful when we're going to use those to constrain the scaling. At larger than 1 second, there is an increased bias, and for larger than 3 seconds, the GMPs start to differ significantly from the GMPs. So that's something we need to keep in mind as we go forward. That's at least for the Western. And references. And we started late, so a couple questions before lunch. Linda? She needs a microphone.
It's just about the magnitude 8 limit. So you said we need to be careful. What does this mean? And until up to what magnitude can they be used?
So based on the only magnitude range we really evaluated is up to 7.2. So that's what we can know that's going on. Based on, and that's a statement, actually I modified this slide from Doug Drager, so thank you for preparing that. But beyond that, we haven't tested it against data, so that's where we need to be careful. As we can use them for scaling, but we need to check within a method, for example, if suddenly there's a kink, well, we need to be aware of that. This was not tested, is the idea. Okay, everybody's tired. Oh, Yucca Mtn, question in the back? Microphone somewhere.
Yusuf Hashash, University of Illinois. For the geotechnical working group, we're looking for a bunch of input motions to use in our simulations. Do you have a set that we can use, or when do you expect to have a set that we can run our simulations on?
Thank you. I didn't put the schedule on there. We want to have all the simulations, the forward simulations, completed by mid-September. We're already going to start using prelim versions. We've ran forward simulations, but we have to vet them a little bit more. But we can keep you posted as we have results that are usable, even if it's not final for the GMPs. Yes. So we have a very tight schedule on this. That's why we started running forward simulations following a validation meeting we had in April, and we were doing new implementations of broadband platform to allow us to better assess those. Okay, so I'm going to say it's lunchtime, and the food is in the back, and I don't have the agenda with me. What time are we supposed to start again? 1:15? 1:15. Okay, so we have 1 hour. Thank you. You can take back the control and change the time, and then put the other guy.